Okay, let's go. I should be live. Sounds good. Okay, welcome back, everyone. Welcome back to the stream. So, on Tuesday this week, we restarted the project by starting work on the code generation part, which is this one big file there. And yesterday, I did one small extra stream to try to make some progress. We did fix a big bug that was introduced on Tuesday, which was nice. However, I got so tired that I was not able to even figure out how to do comparison by the end, so I stopped for the evening. The good news is, and it's always the case, 5 minutes after stopping the stream, I immediately figured out everything that I was blocked on because the second I take a break, I can think about it. I figure stuff out. So this evening, the plan is to resume working on code generation and to try to implement some of the remaining operations that are missing, the comparison operations, fix the problem with branching because we don't have branching yet. Where is that function? There, for now, branch is unimplemented, and I have a plan for how to fix this. And I have ideas for how to also implement some of the more complicated things that are missing, such as function calls. Okay, let's get started. So, first, I've made an assumption so far, and I hope it's correct, which is that the greater operation in Piètre is a strict greater, not greater or equal. The documentation is unclear on that, but I assume that's the case. So here, when we see a greater than operation, we generate an operation which sets the stack to be arg2 on top, arg1 below, because that's the order in which the Piètre greater operation works. Here we do less than by reversing the order of the operations. For greater or equal, we're gonna do not less than, basically. So we're gonna do the same thing as less than with the other way around. So the first argument is a greater or equal to the second argument if the second argument is not strictly greater. So we test that the second argument is strictly greater, and then we do a not operation on it. Which means less or equal will be the other way around. arg1 is less or equal to arg2 if arg1 is greater than arg2 not. Okay? So now here comes a difficult part, which is going to require us to rewrite some of the code in this file. I want to do next the exponent. I'm going to put it here. So we get an exponent instruction from the IR with target argument 1, argument 2. How do we translate that into a series of operations on the stack using the basic bytecode that we have for Piètre? The problem we have here is this is going to be a while loop, basically, in the sense that we have no other way than to do multiplication. This is going to require making a lot of changes because the main big change that we're going to want to introduce is we are going to want to introduce new labels and for go-tos, basically. And that is require keeping track of some state that we're not keeping track of yet. So I think I'm going to take this run bytecode gen thing again, and I'm going to change it ever so slightly. I'm going to change it ever so slightly. Because for now, I have decided that bytecode gen is a state t of a stack with a reader of the hash set of register. I believe this is no longer really required. I don't think we use ask anywhere. We don't. So this is from the previous version of the code from Tuesday that we changed yesterday. So I think this has to go. Although I am tempted to, in fact, rather than just removing it entirely, making it a lot more formalized. Specifically, I think a lot of those things would use the ability to manipulate the stack in a way. So I am tempted to do that. Partly because then if I do things such as keeping the stack in the state, I could also do a thing where I keep the current list of instruction being generated in the state as well underneath. And this would make it easier than just like having to return instructions and get them and append them. This would just be append instructions basically, which would be convenient. And furthermore, I could detect things. I could do things that are smart, such as append a role and then realize, oh, this role does the exact same thing as another role we've done before. Yeah, I think I'm gonna clean this. I am tempted, in fact, not lowering. What am I doing? Generation. I am tempted to introduce generation monad. And start writing some structure code here. Specifically, when generating the code for a block or for a function, is there anything that we need? Because I think I'm basically going to, at this level, do a run and have everything operate in this monad here. So this will be, I'm just going to see how I named monads in previous generations, in previous stages. For instance, the analysis monad, how is it named? Validation monad is name validate. Okay. So I assume then that the one for resolution is name resolve. It is. Okay. So that's the naming scheme we have so far, which means this is going to be the generate monad. Did I use new type for the previous ones? Or just type? Yeah, just type. Okay. So generate of A will be a reader. Again, I have used, let me check that again, info for the reader, context for the state usually. Let's try to keep the name consistent. So this will be a reader T of some generate info over a state of a well, generation info and generation context. That feels like a reasonable thing to have, which is very similar to what we have here. I might, in fact, use this opportunity to change what is a stack, because so far we've been using a list, which is absolutely horrible. And I think we want to use better than that. Do I want to make that a data type that is a record that keep track of several things, or can I just use a type alias for this for now? What do I need? For most things, I need to know the ordering of things in... I think a sequence is probably fine. Yeah, I think I might even go one step further. and make a new file for the stack itself. Maybe something like this. That way, now the rest of the code just uses operations on stack as an opaque type, more or less, and every operation on stack goes in this file, which means if I ever realize, oh, I keep doing indexing of things on the stack, I could keep track of a hash map from register to indices or something. I can change this to a record, and none of the rest of the code has to change. So I think I'm going to do something like that, which means I'm going to need, is it data sequence? It is data sequence. Although sequence might already be in scope, so I probably just need the IR. Now, if this is a stack, we are going to need a few basic operations. Such as push will take a register, a stack, and return a stack. And push of a register and a stack which contains the actual underlying sequence is simply a stack that is R at the beginning of said sequence. I am gonna need indeed to have a sequence qualified as S, I think. And I'm gonna probably want to also import some of the operators, such as this one. Okay, I will probably want to have a basic pop operation. Which in this case will be a partial operation, I think. I think I'm okay with that. Is there a drop, actually? There is no basic drop? Interesting. Oh, there is, okay. Yeah, I think since I don't rely on this container for complicated things, I think I'm okay with saying that if we try to pop a stack and it's empty, nothing happens. That's an error somewhere else in the code. I don't think I really need to take care of it at this level. So I think I'm okay with just saying drop one of the sequence. I will probably need the size, which given the stack gives me an int. The size will be just the size. Is it size or is it length? It is length of the sequence within. In fact, and let me check something. What's the complexity operation of length? Because if it's not constant, I could change the type to keep a copy of the length, which might come in handy. Oh, 1. Okay, perfect. That's already so much better than list. Now, There's a few things that we might want to add to this. We will want to, because again, the idea of this is ultimately the stack type will, that this will be hidden from the imports, from the export list. So the rest of the code will only be able to deal with a stack with those basic operations. So I will probably need something like contents, I think, that for a stack will give me a hash map from register to int, which is the amount of times a given register appears within the stack, which is something we've used in the past. So given a sequence within a stack, this is a map from list. Oh, annoyingly, is there a way to get this without making a list? Could I do this as a fold, perhaps, instead? Because I assume data hash map strict, the from list is not something that does a fold thing. It is an actual list. Yeah, it's an actual list. So maybe I could instead do some kind of, because I assume sequence has folds. It is probably foldable. It is, okay, UR is foldable, but it is foldable. Okay. Which means I can do a fold map of it. I cannot do that. The union of hash maps discard things, but I can just do a regular. Unless there is a specialized fold, maybe I want to use a specialized fold on the sequence. Okay, no, it's just the foldable stuff. So let's go for a good old fold L prime. This is gonna be a function that takes the map. Okay, so I'm just gonna make a step function there, and our starting accumulator will be an empty hash map, and we are iterating on the sequence. And what do we do at every step when we have a map and we have one value, one register R? We insert into the hash map with plus of that register and 1. I'm almost tempted to do a flip step here so that I can do that. But maybe that's not required. Okay. I will need, as usual, data hash map strict qualified as M. Okay. Next, what do I need? I will need an inspect, which given a stack and an int, which is an index, will give me maybe a register. Okay, I'll just put this away for now. And that is just, just gonna look at it again. I assume there is an indexing function in this somewhere. Indexing, lookup, perfect. It's still not instant lookup, but it's not too bad. or this operator, but I'm okay with lookup, which is going to be index in the sequence, I suppose. Okay. What else will we need? We will probably need a role. If I go back to the generation code as it stands, whenever we get the stack, like in this big rearrange stack function that we made yesterday, that works, but that is ugly and that I will want to change. So that's the hash maps from the list with plus. That's the same thing that we've been doing, the contents function. I think the main thing is the role stack. There we go, where we actually do a role. Okay, so that I think is the other big function we're gonna need, because that's the main way we modify a stack. In fact, I think I'm gonna modify like this is just do I want to make an instance of is list? I am tempted to do that. This might not work with a deriving, but how do I create a stack even if I don't know that it is a sequence of register within? Then I just need to give it a list literal, basically, or do a from list. That feels reasonable for creation. Then querying, size, contents, inspect, modification, push, pop, and roll will be the only things that are required. Roll will need int, and we'll take a stack, return a stack, and roll will be given the depth and the number of steps and the stack. It will be, and this is where I need to have a look at, would it be faster to swap elements or to do... Because another option is not to use a sequence at all, it's to use a vector. But I don't know how much vector scales with like changing the size of the vector dynamically. Let's see. Read size. I want to know the performance constraints of this. Yeah, prependent element, appendent element are of n on the vectors. So unless there is a way to reserve space ahead of time, which I think there might be, for a stack this might not be great. Is there a way to... Yeah, I think if I were certain that there's a way to guarantee, maybe this would be better. For now, I think we just use a sequence. I'll have to look into the performance consideration later. Already not using a list will be so much better. Okay, so now what I want to see is there a split on this? And what is the performance of that? It's not too bad. Okay. So we can probably just copy what we had before, which was on lists. And do that here. This stack is a stack that contains a sequence. So we get the top of the stack and the bottom of the stack by splitting at the depth. Then we get segment 1, segment 2 by splitting at steps, the top of the stack. And the result is a new stack that contains, I'm just gonna align this differently. Oops. The segment 2, then segment 1, then the bottom of the stack. There we go. Okay, so now we should be able to use this stack type, and I think I want to guarantee this immediately by doing an export of stack, but not its component. Size, contents, inspect, followed by push, pop, roll. That's about it. And the key thing is, again, that part is now hidden from the rest of the code. Let's see if this module compiles on its own already. I started working on this and I did not finish it. So for now, this is going to be empty, which means it's going to complain about this, which means, there we go. Not in scope is list. Okay. Where does is list come from? Again, I think it's a GHC import because it is a language extension. So if I look for is list in here, there we go. It's GHC is list. Okay. Think about it, the deriving may actually work since this is just a new type. If it were not a new type, it wouldn't, but this is probably gonna work. Okay. Insert with typo here. Ah, okay. How is that an undecidable instance? Fascinating. Let's see how it's implemented for sequence. Come on. That's fascinating. Why would that result? It's no smaller. Let's see if I can instead do this and make it myself. Can I avoid the undecidable instance? The type of an item of a stack is a register. And all three of those will be doing stack of from list. Okay. Hiding to list. Oh. There we go. Would I avoid the undecidable instances, or is that still a problem? No. Okay. Aha. Yes, okay, that's the wrong number of arguments. Which means I am very tempted to just use this operator and not explain further. Okay, so now it's the issue. Yes, of course, I'm an idiot. That's not how that works. This would be given a stack that contains a sequence. This is to list of the sequence. Okay. Okay, so now this seems to compile without actually requiring undecidable instances, which I think I prefer. Now, what are you unhappy about? Is it that, yes, I was using the split at from the prelude, therefore the one on list? Okay. Sequence is something that will conflict with another name, of course. So let's rename it stack everywhere. Okay. Yes, okay, so we're back here. So now this seems correct. Great. I'm gonna do this and go back here. I think I'm fine with it being a bit small on the size here. That's fine. So here, what we want to do is go back to doing this. What will we have in our generation info? What is the stuff that needs to be, do we need to keep track of that will not change within the scope of a function being generated? I think the only thing that is actually required is the function name. I keep this here. I keep this visible here. It's a bit small on the screen, but it's more to have it on the stream. This is going to be the main window. It's fine. I wanted this. Okay, so for now, the only thing that I'm going to require is going to be the name. That just is convenient. And now, what do we need? What do we need as the generation context? What do we need to keep track of? I am tempted to put two things in there for now. The instructions, so like I don't have to keep have each function return a new sequence of instructions that needs to be appended together afterwards. I can just in the state have my current buffer of instructions, basically, which will be a sequence of be this from here. Of instruction unresolved. And I might not need the import here because this will not deal with the IR much, I think. That's actually not correct. I will need to know about registers, probably. I will need to know about stages generation stack. Okay, so we need the instructions, and we need the current shape of the stack, which will be our new stack type. Okay, now with this in mind, what can we do? We can move some of the code that was, I'm gonna remove this from now, for now. We can move some of the code that was in here to instead being operations inside that monad. For instance, I think all of this rearrange stack thing will become a function operating in our monad of like, oh, given the current state of the stack, give me this desired shape of the stack, basically. By appending the proper instructions to the set of instructions, and by also keeping track of the stack within, which means we are going to be able to move this big function and clean it. Is there anything else that we need to do? No, this annotate stuff will remain where it is, I believe. That doesn't need to change. Likewise, this doesn't need to move. I think, yeah, applying this apply operation thing that is horrible will move as well. Okay. For instance, what do I need? Oh, I need also, I will need, what is the syntax again? Let's go back to a previous monad thing. Where are, I don't have lenses for this? Oh, I do. There we go. That's what I was looking for. Okay, which means I need template Haskell. And I need to import control lens. Okay. Now, with this, what do we do? We will probably want a few basic operations. I think ideally I would like this to not be visible from outside of this module, so that the code that does the generation is limited to, I have this context of instructions and stack, and now give me a new thing. I think I will want to use a bracket-like thing to initialize and maintain the scope for a particular. I don't think I will ever need to stack contexts, because I will never need, I believe, to start appending more instructions. Across blocks. I don't think I will need to do that. That means I can probably do something like this, a with block, which is going to be a function that, given some block coming from the IR, maybe I leave the details of this. Give me 1 sec to think about this. Because here what I do is I do each block in isolation, because each block has a starting stack and a desired stack at the end. So each block should be done in isolation. That being said, I could use the exact same buffer of instructions inside, rather than maintaining a bunch of different buffers. They would probably be more efficient. So what do I need when I do a block if I do that? I just need to start the stack in the correct and the stack starts with this basically. Is there any benefit? So what I was thinking is basically, do I have a function that does something like this, given a block and an action in the generate monad gives me a wrapped action in a generate monad that does all of the bookkeeping on the stack and the instructions and everything? Do I need to do that? Or do I not care? And I think I can instead do something like this, starting with, which will take a list of register, which will be the start of our stack, give me an action in a generate monad, and return an action in a generate monad that doesn't return anything because it puts all of the instructions into the buffer. Or maybe, do I make it return a copy of the buffer? Do I do concatenation at a later stage? Nah, I think this is fine. I think this is fine. The only reason I would have to not concatenate all of the blocks in one big buffer would be if I want to do reordering later, which in fact I might want to do. This might be better. Yeah, so maybe in fact this gives me... I am tempted to introduce a new type for this. I use sequence of instruction everywhere. Do I want to name this thing in the same way they have name stack something? Maybe a sequence. In fact, the type here is wrong. This is the type. Maybe this is simply a instruction buffer. Which means I could do this as starting with, well, generate with is a function that's gonna take a list of registers. Generate with is not a great name. What would be a better name for scoping the context of something? In fact, now generate with is growing on me. I think I'm gonna keep it. So this takes a list of registers, which is a starting stack, an action in the generate monad whose value I don't care about, and gives me the corresponding instruction buffer. Okay. With I get the starting stack, which is just a list of registers, and an action. What do I do in this monad of mine, I will set the instruction buffer to an empty list. I will need there again here. I'm not going to use the overloading of list syntax. I'm going to be explicit. And the stack starts, and I'm going to use this qualified as stack and here as sequence for clarity. And the stack will start as stack from list of the starting stack. This is what the shape, what the stack looks like at the beginning. Then we perform the action, and I void the action. I don't care about its value. And I return use GC instructions. Okay. Okay. Next, what do we need? I will probably want to do an append instructions, which given a basic list of... Can I make this generic? I think I probably want this to be an instruction buffer, as in already a sequence, but it can probably be inferred using the from list thing. So append instructions will be an action in a generate monad. And append instructions is just given some new instructions, is just modify the GC instructions And how do I modify them? I modify by doing this with the new instructions, and I believe there is an operator for this. So let's have a look at lens setter. I think it's something like this. But there's another one. Because there's one that puts at the beginning as well. And I want to check which one is which. No, okay. I thought there was one. I'm fairly certain I've used it in this somewhere. Yeah, this one. Oh, it's in control lens operator. There we go. It prevents the head side. Okay, yeah. But I think in this case, we want to append at the end, so I can just do that. New instructions, which means I can even simplify it to this. And I might rewrite as this operator applied on the lens GC instructions. There we go. That's the simplest possible version. Next, what do we need? I will probably... I will probably want to... The problem with this is I want to keep the shape of the stack and the instructions in sync. So that means I should probably, when I do that, when I do an append instructions, either I provide an API such as append push, basically, that will shape the stack accordingly at the same time, or whenever I do an append instructions, I need to run through those instructions to simulate the shape, to simulate what happens to the stack, basically. The problem is I will not always be able to do that. If I were able to compute the entirety of the program at compile time, things would be different. I guess the shape of the stack I should be able to. Well, will there ever be a role that is dependent on runtime values? Probably not. Yes, there will when I have dynamically sized data. Okay, so I think trying to do this at this level of like I analyze the instructions that I'm pushing. So I'm gonna label this as unsafe because this will change the thing without changing the underlying stack. However, append role will be a lot better because this will be given to ints do a generate here, and this append role for depth and steps will be add to the instructions push int depth, push int steps role, and modify the stack by doing a stack roll of depth steps, guaranteeing that now this is always kept in sync. And I can do something even better, which is I can check if depth is 0, then this we do nothing. If depth equals steps, we do nothing, which means here, rather than doing an optimization pass later, I can immediately detect that, like, oh, we have generated a role for reasons that makes sense in the context, but this role happens to do nothing. We can just ignore it. That's convenient. And otherwise, then we do all of that stuff. And I guess something we could try as well is let's get the last 3 instructions. How do I do that with a sequence? I will want to do a take R, basically. Does that exist? I'll probably want a view R of the thing. So I get a view R of the sequence that gives me this. There's no generic take on this, I suppose. It's a bit annoying that take and drop don't exist on Ah, it is annoying. Okay. So that means we're gonna have to do it ourselves. Unless foldable, traversable have something in there. Does foldable have a version of take? See a few matches down the line. Or is it always the take of list that is used here? That seems to only be... Yeah, that doesn't seem to be a way to do a generic take on a foldable. I suppose that makes sense. I would need to know, but yeah, okay. So let's do it manually. I will need last n instructions will be a function that given an int gives me inside our generate monad a list of instruction. And this will be done by doing we get the list, so instructions. This will be a go of uses gc instruction, and we do a view r, which is the function in here that gives us a view, a right view of the thing, which will be that. Where are you, view r? This one, which gives us one thing like this. And then annoyingly, we're gonna have to write this a bit manually, but that's fine. Can I write this point free? Probably, but it's not required. So this would be go n of a view r, and it's either the empty r, I believe. Yep, in which case we return in fact, I will probably want to create a buffer as I go. So this is going to be this and a buffer here. This is going to be returning just the buffer regardless of the size. Otherwise, so I need to have the base recursion here, which is this. We return the buffer. Otherwise, if it's empty, we return the buffer because it's a take. It doesn't matter. Otherwise, if it is whatever that thing is, it's that. This is go recursively with n minus 1 with a buffer that has been appended to contain that value x. I guess I could just get them in the reverse order. I think it doesn't really matter. In which case, this is x at the beginning of the buffer. And we go on the rest of the sequence S. There we go. So now here I can do, give me the last 3 instructions, which will be last n instructions 3. And now I can do a case of last 3, which means I can rewrite this as a bind into a case. And in the case where we got roll push int s steps prime push int depth prime, because it is again in reverse order. In that case, and when depth equals depth prime, so we have 2 rolls in a row at the same depth. In that one case, we can do nothing. Well, not nothing. No, that's not true. That's not true. It means... Is there a drop at the end? There's no drop at the end. Oh, this is annoying. So I will just need a split. Okay, so I'm gonna do this completely differently, in fact. Um... Oh, this is probably faster than doing a split. Okay, so let's keep it that way. So this is the case where we can merge the roles because they're the same. So what we can do here is get the instruction buffer all together. Just use GC instructions. This will be a sequence split at of sequence length of the buffer minus 3 of the buffer. And we will put back a new version of the buffer, which is b4 plus push int depth, push int steps plus steps prime modulo depth. Roll. Okay. And otherwise, in any other case, then we're back to this, where the instructions before were not a roll, therefore... come to think of it, there are some more optimizations that I will want to do at some other point, such as arranging the blocks in a particular way, removing labels that are unused. So maybe this kind of fusion of the roles will have to happen at a later stage to make sure that I get all of them, which means this is still worth doing, I think, but I might remove this for now. So this is probably not required for now. Oh well. Now, what else? I think I would like to move the details of this function rearrange stack here, because I think I would like I think, to be able to move this apply thing here entirely within, because most cases this will be, I want the stack, hello, how are you? I want a stack to be in this particular shape to then apply this thing that pops the stack, basically. Which, again, as much as possible, I would like to have confined in here so that I can guarantee that both, whenever an instruction is pushed to the buffer, the internal model of the stack is kept aligned with it. So I think I might want to move all of that into that file to keep it. So this would become this whole thing that we wrote yesterday, which is way too big of a function, comes here. And it becomes a new, it gets a new name. This will be what will this be? I think rearrange stack is not the worst name. However, it will change to now just be a function that takes the desired stack and returns an operation in our monad that does change the internal representation and pushes the new instructions to the internal buffer. So now this becomes, rather than having to keep track of instructions and the stack and everything, this becomes this. The input registers are not required, although it would be probably good to have. So let's go back to stack. This is the contents that we've been making. So this starts, this is currently stack content is uses gc stack, and we apply stack contents. That feels reasonable. This does not require the sequence being there anymore. This takes the stack contents that are going to be updated as we go. Do I keep, because here I probably don't need to keep track of the stack. I can probably just use the roles and everything as I go, so I probably don't need to give it the starting stack. So I probably, however, need to give it the target contents, which is, I'm gonna keep it named. It doesn't need to be named. It's just for clarity. That is the stack contents of the desired stack. So now we do this clean, which was this before, which now doesn't need to give us the cleaning instructions. They will be appended to the buffer. Doesn't give us the unsorted stack. It is already the one that's going to be within, so that's fine. So we can remove that. This feels unnecessary. I'm just going to remove this. Just name it here. Okay. Then yet again, not having to do the reverse and everything because I'm not going to have the buffer, this is going to be this map accumulator is using the stack. This is no longer required. This is now basically... I keep this zip, the 0 and the desired stack, I think. Oh, except now I will need that as a list, I think. I zip that with 0. That gives me for each thing in the stack a given index. I reverse that, and I can then traverse it with this roll stack register. And I don't need to do the accumulator that takes the unsorted stack and everything, because now the stack is part of my state. Okay. And now all of this goes away. Okay, so that's better. Oops, I was a bit too eager. This goes away, and this goes away. Now, clean. Clean is now a lot different. It doesn't require knowing the instructions. It takes the hash map of register to int, which is the desired stack, which is the output registers in the thing we have named it so far, and it takes the current registers. And this is an action in the generate monad that doesn't need to return anything. Okay, so this requires me having a look at the top instruction in the stack, okay? So that's something we haven't moved here. I will probably need... Well, I guess this is inspect 0. I suppose I could create head that, given a stack, gives me maybe a register. And head will be... Do I want to flip this ordering? Maybe, in fact. And this is inspect 0, basically. Oh, I need to export it from this. So this becomes now clean is a function which I might rename, in fact. This will be adjust stack content. Adjust stack content will be this thing where it takes the desired content, current content, and will do a bunch of things. So first, we get the register R, which is the head of the stack, and we get this from the current GC stack. Now, I suppose if the stack is empty, there is nothing left to do. Which is what we do. This was for. So yeah, I suppose I could just do that into a case. If it's nothing, then we pass. We have nothing left to do. Otherwise, if we just get a register R, then well, I suppose first we have to check. We have to check that. That's the end of our recursion. A question about the generate monad. So this generate thing is just a name for reader of generation info and state of generation context. And generation info is just currently a function name, and generation context is the buffer of instructions and the stack. So you can see basically a function such as this rearrange stack that takes a stack and returns a unit in generate. This is the same thing as a function that takes this stack, which is an argument, takes a generation info, takes a generation context, returns the new generation context with some modifications, and whatever this value here is, which happens to be unit, which is useless. So you can see it as a function that, given a stack and some info that is accessible, takes a context, returns the new context. So what the statement, this generate monad is mostly about keeping track of this state, but I don't have to do the thing where I take it as argument, return it manually at every step. I just say we are in a generate monad, and like I used the properties of the state monad for that. That's the goal of this. And it makes like the code I'm replacing from yesterday. Basically, now I can just say adjust stack contents, and now after this, the output of this will be the new state that contains the new sequence of instructions and the new shape of the stack. While yesterday, if I copy this function back here, I had to get the output of it, which was the new state of the stack and the instructions, and then manually give that new unsorted stack as an argument to the next step. Now all of that chaining is done for me automatically because I am just using the state monad for this. And basically, whenever I want to add more things that all functions have access to or more state that can be moved around, I just modify those two records here. So here, that's still our, except it's no longer than the same. If the current content is the same as the desired content, then pass, we have nothing to do. Otherwise, do. And this is where we do this. We look at the top register of the stack. If the stack is empty, there's absolutely nothing to do. Otherwise, we have a register R. And this is now going to be mostly the same code. So I can just keep this as... Yep, basically. The idea of having this state alongside is like most of my code here and the code I want to add needs to keep track of, okay, what instructions have I added to my buffer and what is the current shape of the stack within this part of the code generation. So if I make a bunch of functions such as append roll that do that for me and do both at the same time, this append roll, given depth and steps, just performs an action in generate that adds those instructions and modify the stack. I don't need to make sure that I keep track of it manually in all the rest of the code. The rest of the code can just say append a roll, and all of the internal state is kept correctly. So now this hasn't changed, we do a lookup of that register in the desired content, and we do a minus on the current content that tells us how much should be added or removed of that register. I don't need to do a let in because I am now in a do block. And I can do this if delta equals 0, we have nothing to do, I think. If delta is 0, we append roll. Aha. This is an append roll on the entire stack. I probably want a few things. First, I probably want some accesses such as stack length or stack size, which will be a simple int in my generate monad. Stack size is simply uses the lens to look at the stack and apply the stack size or length. How did we name it again? Size. And I suppose I could do a append full roll. That feels ugly. Because I want to avoid having to query the stack size and give it an argument, because there will always be a risk of, whoops, I'm giving one that is out of date. So maybe a full stack roll here like this that just takes the steps. And what it does is it gets the stack size and does a append roll of that depth and the number of steps. This could be probably made 0.3, but there's not really a need. Okay. So that means here, in the case where delta is 0, this is append a full stack roll of length 1, which is not entirely true. This will need to be the size of the register, I suppose. Which is, and I need to continue cleaning recursively. I'm just gonna, there's so many things that will be broken the second I have non-1 registers anyway. Still, to do, handle handle bigger registers. And then we go recursively to adjust stack content. Our desired contents haven't changed, but our current contents have. They have not, because we haven't had to do any delta. The stack has changed, that's all. Okay. If delta is greater than 0, I'm tempted to actually make this case the otherwise. We had the weird thing where the compiler was not able to see equal 0, greater than 0, less than 0, and realized that covered all cases. So I think I want this to be the base case. So I'm going to make this the otherwise. I'm going to make this the delta greater than 0. and then delta less than 0. Those are the interesting cases. Okay, so less than 0 means we should be removing this register, which means yeah, I think this is, it's still happy with this. I'm just gonna comment it out and make that a pass for now. Just that's my, yeah, there we go. So in this case, it means the register needs to be removed. What do? We will append an instruction. So the GC instructions will be modified by appending a pop instruction. And the stack will be modified by doing a stack pop. And I will go recursively to adjust stack content with the desired content unchanged, to the point that I'm tempted to make it maybe not a reader or something, but it's fine. And now our content is this new update, subtract, or delete of our register R in the current content. This doesn't need to be changed to handle bigger registers. I think that's fine. No, it needs to be changed because the amount of pops here will have to be proportional to the size, will have to be the amount of the size of the register. Because if I'm popping a string, then I will need to pop all of the elements of the string. Okay. That will be a lot more complicated, but that will be a problem for future me. And here, what do we need to do? So first, that means we need to add a bunch of duplicate instructions. So that will be GC instructions gets modified by adding a so replicate will be, so I will need a sequence replicate of, well, right there. I can just copy that. So that's the new instructions that we need to append, which means the stack gets modified. Do I have anything? I don't have an easy way of doing a bulk modification on the stack. So maybe instead, let's do it this way for replicate M is what I want, I think. I want, given an int and some kind of action, give me the action replicated. Replicate M, there we go. I want to replicate M delta, something which is push a duplicate to the instruction, modify the stack by doing a stack push of R. There we go. And then I will need to recursively go again to adjust stack content. Desired content hasn't changed. But here we will just adjust with plus delta. Okay. I am tempted to, instead of a multi-way if, do a case compare delta 0 And now this is the GT case, this is the LT case, and this is the EQ case. Reduces a tiny bit the indentation and avoids a catch-all otherwise. Okay, that should be better. So, we're trying to adjust the stack content. We peak at the maybe peak instead of head. That's fine. At the top of the stack, if there's no register, we have nothing to do. Otherwise, we look at the amount that we require compared to the amount of time this register appears. If we need to add to replicate it, we add a bunch of duplicate instructions and we push new copies of it. And this, yeah, I'm gonna also add this here because this will need to be multiple duplicates when I have registers that contain more than one cell. Likewise here, we need fewer, we pop, and that's fine. And here we just do a full stack roll. Wait, no, there's something that's wrong here. When I do this, I need to do a roll as well. I have removed. That is wrong. Okay. If I go back to here, I do that, and I look at what I was doing here in the case of greater there. Here, I was doing a roll stack of the full stack by a number of things I have added plus 1. So I need to do the same thing here, which is append a full stack roll of size delta plus 1. Okay. So that's the adjust stack content. Subtract or delete remains. That hasn't changed. And now roll stack register will have change. Because it doesn't do, see, this was taking the stack, returning a tuple of the stack and the instructions. This is old state, new state. Roll stack register is a function that takes an int. In fact, I am even tempted to do an uncurry here. Roll stack register is something that takes an int, a register, and perform an action in the generate monad, which is the one that keeps track of the stack and the sequence of instructions. Okay. Let me just think about this for 1 second. This probably needs to be a traverse underscore. There we go. Now, this was the function that like, okay, we need to look at the register at this index and it needs to be correct. If it's not, we need to do a roll. So we can probably see roll stack is no longer required. That's good. Find register, I am going to move this function away from this. This is going to be here. I'm going to add a new function that given a register and a stack gives me an int. No, Can I assume that looking for a register will always... Yeah, there should never be a case where I use this find and the register is not in the stack. So I think I'm going to keep it as an int, not a maybe int, and keep the internal compiler error at this level. So trying to find a register in a stack, which is a sequence underneath. Oh, does sequence have an LM index? It does. Leftmost. Perfect. That's exactly what I want. Okay, the report ICE doesn't need to change. I'm just gonna copy the name of the import out of sheer laziness. Oops. Okay. I want to name this thing something else. I don't like the I think that's better. Okay. So now we can go back to what we were doing, which is here. This roll stack register is I look at the stack, I look at the register. Current register will be the result of looking at the current stack and doing a stack inspect of the index. If current register is just R, then pass. We have nothing to do. The correct register is already in the correct place. Otherwise, first index will be a stack find of R, which we do again on the current shape of the stack. And we can do a append roll of the depth, which is I plus 1, and the number of steps, which is first index plus 1. And I'm going to probably rename this I, because I don't like this. Target index. Okay. So now, not only is it a lot smaller than yesterday, we've moved a lot of stuff to other functions, it is also probably easier to read because now all of the state passing is done using the state monad rather than manually getting the result of the previous function call and giving it as an argument to the next function. The downside is now this needs to be called within a generate monad. It cannot be used in isolation, but that's fine because this is not a monad that's complicated to use. Okay. So now rearrange stack is there, which means we can move one last function from here, which is this poorly named apply operation, which I'm going to rename instead append operation. And this will take I think I want to change it to be basically the equivalent to this. So let's copy that as well. So append an operation. What do I want? I want to know what are the arguments to the operation, which will be a list of register. I want to know the target, which is the first register. So I'm going to actually do that. Target args. But I will need to know which of these arguments can be moved and which ones need to be duplicated. And this will depend on a particular thing, which is called here output registers, which is a hash set of registers. So given this context of a hash set of register, a target register, a list of arguments, and a sequence of instruction, which is just an instruction buffer, give me an action in the generate monad. What does this do? So this will be output registers, the target, the args, and the bytecode. This is going to be more or less this, I think. We get the current stack, which is this. Our desired stack will be... Oh, but this is treating the stack... Aha, so that means... This is breaking the encapsulation. I have made the stack a dedicated type here so that I don't know its internals. But I think it's fine because this is explicitly a list, which means this is stack to list of the current stack, which I can even do a uses gc stack to list. I filter the current stack to only keep the ones that are a member of the output registers. I add the arguments, which means then I can do a rearrange stack into that shape, which gives us the instructions, gives us everything. I don't have to keep track of the instructions myself. After which, what do? I can change the instructions to be appended with the bytecode. And I know that all operations like this, append operation, are things that modify the stack by doing this is replicate m length of args apply stack pop to pop the arguments and then modify the stack to apply stack push target. There we go. And this takes care of everything we've done so far. So append instructions unsafe just allows me to put more instructions on the thing. Append roll does this full stack roll do a roll with the full stack size. operation given a list of registers that need to survive, a target register, a list of arguments, and a bunch of bytecode will rearrange the stack as required, append the bytecode, pop the stack, push the target as required. And rearrange stack is a slimmed down version of the thing we did yesterday that, given a desired stack state, computes the operations required and change the internal buffer. So now all of the stack passing that we were doing manually yesterday is gone. That means we can go back here and change everything for the better. So this is going to require access to the monad here. So this will be, I probably want to add actually a run generation thing that, given a function name for now. What have I done for previous monads that take an info? Do I just take the info? No, I take the arguments. Okay. And some value in the generate monad, excuse me. What do I need here? Can I make the assumption that I don't care about the value whatsoever and I only care about the buffer? Because yeah, at the end I only care about the buffer. For now, I think I can just make the assumption that the only thing I need is the instruction buffer out of this. So running the code generation will be given a function name and an action will be run the action and run flip run reader t of a generation info that contains the function name and nothing else, and flip exec state t. I never remember which one is which. That's something I have to check every single time I use the state monad. Between exec and eval, which one gives me the value, which one gives me the state? Ah, come on. Is hackage done again? There we go. I want eval gives me the value, exec gives me the state. In this case, I want the state. So exec state. And the starting state will be a generation context that contains a empty instruction buffer and an empty stack. This will require the overloaded lists extension. This gives me at the end of this the state, and I extract the buffer by doing a gc instructions at the end. Okay. So now I can go back here. This function becomes run generation using the function name. And what do we do? Well, for every block, there's probably some more operations we want to do, but for now this is going to be good enough. This is going to be a for each of the fun blocks of this function, which gives me a label block. What do? I do a with, a generate with, which starts, So this goes away. Do I do this at this level? I think I might do it at this level. Maybe not. Maybe not. Maybe this is just generate block byte code with that takes the label and the block. And that's about it. Generate block byte code. Doesn't need the function name anymore. It takes the label and the block. And what it does is append instruction unsafe, and that is an entrance for this particular label. So we already immediately need the function name, which we get by doing an ask. It's going to be used for other things, which is why I've put it in the reader rather than just giving it as an argument here. Append instructions unsafe, and we are appending just entrance function name label. Okay. And then we generate with the stack, which is the block arguments. That's the shape of the stack. Do I actually want to change this generate with? Yeah, I think I might change this. This is an eval state here. Which means this for thing will be... So this becomes instead blocks code is a traverse with uncurry generate byte code of the fun blocks. And here I do something with it. I will get a list of buffers, because I do reset the buffer every time I do a generate with. Yeah, okay. And so here I get the list of the buffers. For now, we can just pure fold the blocks code. But this is where I will probably do a pass of optimization that detects roles that do the same thing more than once and tries to rearrange the blocks in such a way that I can remove jumps and labels when they're not required. So yes, I think it will be something like that. So generate block byte code, takes the label and the block and gives me a generate of an instruction buffer. And this is an instruction buffer there as well. I append an instruction, so we generate with the block arguments. I append an instruction unsafe, which is the entrance. That's fine, it doesn't modify the stack at all. Then so we're gonna keep this. That is still correct. This annotate instructions function will remain. It's the one that, given a terminator and a list of instructions, give me a sequence of the instruction and the set of registers that need to survive that we've been using so far. So this remains. Oh, rearrange stack goes away. I thought we had already moved that. However, a lot of this will go away and be simplified, because now what we do is, why do I use a map accumulator? Because I'm keeping track of the stack. I'm keeping track of the stack, which is no longer required. So now this is purely a traverse with generate instruction bytecode of the annotate instructions of this. That's it. All of the rest of the stuff is just stuff that was state passing that is no longer required. And I might just do an uncurry there as well. And that's a traverse underscore. And at the end, I will just need to do a generate terminator bytecode, which doesn't need the function name, the final stack, and just needs the block terminator. Okay, so this is a lot easier now. Now, generate instruction bytecode is something that no longer needs to do the state passing manually because, again, this is just a statement. Now, this is something that takes the instruction, the hash set of register that we've been using to keep track of what needs to be duplicated and what can be moved, and in this case gives me an action in the generate monad that doesn't need to return anything. So stack is not given, that's not required. Oh, do I want to flip that? I am tempted to flip it. Unless I change my annotate. I'm changing my annotate to have the instruction as the second argument there. Up, there we go. And the reason I'm doing this will become obvious in a second. It means here I no longer have a stack argument. I have the output registers argument, but now this is just a case on the instruction. And all of those are now just, this is append operation, target argument bytecode. This is all the same. So I can replace all of those generate operation oops, by the append operation function we have created. That's done. Perfect. This function goes away. And now generate terminator bytecode no longer requires the function name to be given as an argument. It is passed as part of the monad. The current state is no longer required. The only thing we need is this is something that, given a terminator, performs an action in the generate monad. That's it. That's not nothing else. And in the case of a panic, this is just append instructions and safe of a terminate. Now this is where it's going to be interesting. because this is not going to be a simple append operation. Or is it? No, it's not. Okay. So this is a rearrange stack to match the target arguments, followed by append instructions. Unsafe is not a great word. It's not that unsafe. Unchecked. Append raw instructions. I think I can just call that append instructions. I think it's fine. Okay, unsafe. There we go. So here I will need the function name, which is in the context, well, in the info, which is there. So a jump is rearrange the stack to be in the shape of the arguments of the jump, push the address of the jump, and do a return. A return, I'm going to change this at some point, but for now, this is correct. This is pop the entire stack. So this is a replicate M. Do I want to do a clear stack, basically? Well, this is a rearrange stack empty list. Technically. That feels a bit gross to invoke the entirety of rearrange stack when what I just want to do is insert pop operations, basically. But it will result in just pop operations, so this is probably the simplest version. Append instructions. Return. A return with just one argument is a rearrange stack to just be that one argument. And then it is an append roll of depth 2 and step 1 to do handle bigger registers. And then append instruction return. This append roll to 1 is to put the register right there below the return address that needs to be on top of the stack when we do a return. And now, with everything that we have done, we should be able to implement branch, and we should be able to implement some of the weird instructions that we haven't done yet. I'm just going to do this as unimplemented for now. And there is some stuff that we're going to need to add to our state there for that purpose, which is the reason why I went through all of this refactoring, is we are going to need to keep track. We are going to need to keep track of sub-label index, which is an int. And that will start at 0. In fact, it might start at 1. And I will probably want to have a function that will give me bump. That's 0, it's fine. Bump inner index, which gives me a new index after bumping it. And bump inner index does modify GC sublabel index by doing plus equal 1 and just return that sublabel index. Okay. And with all that done, I can even go one step further. I could do a push new entrance. I'll see what I need when I get there. For now, let's make this compile. Okay. Yes, I've changed the order of the arguments here, but I did not change the names. It's fine, it's gonna be fixed now. Interesting. Define but not use find, but that's because I did not add it to the export list. Parse error. Case of stack not in scope. That means I did not. Yes, I suppose I probably want to also just import the stack name as such. Function name is not a thing, that's a name. However, indeed, I'm gonna need the IR in scope for the other things. Aha. I am using toList and FromList as if they were exported from... But they can be, in fact, since I have import data foldable in scope. I can add them to list and from list to the list of the things exported from this module. I think that should be fine. Except it's not clear which one, but it's probably fine to not use the one from foldable and use the one from isList. Okay. There we go. Now here I am using this set member thing. I'm gonna name it explicitly, but I don't have a thing named set in scope. This is because I need data hash set qualified as set. And maybe I'm going to revert to my usual names for consistency, where set is S and hash map strict is M. That's how I've named them in basically every module in this project. Let's be consistent. Okay. So now generate is not in scope. That's probably because I did not import the monad module at all. So everything here will be broken. Let's fix that. Oh, because I am in the wrong module, so I've just created a circular import. Why does it... Is it a lens problem? Oh, expecting one more argument to generate. Yeah, of course. Here, this is, I was reading the thing wrong. target index. That's a typo. So the args are a list of register. And I am creating a list here. That means I should probably do a stack from a list here explicitly. Okay. Int with maybe int. Ah, yes, this is not an update because update is the wrong one. This is, where is hash map strict? There we go. It is adjust that I want in this case. Okay. Okay. Entrance is applied to two value arguments. Yes, an entrance actually takes just a tuple of function name and label because it takes an address, which happens to be that. Yes, here I'm doing an ask of the entire generation info. What I want is to view the generation info function name. And I'm going to have the same problem for the other place where I get the function name, so might as well go fix it now. There we go. View. I don't have... Oh, that's going to be a problem. I need control.lens for basically everything. Okay. Did I not fix the type? Oh, yeah, I did not fix the type. There we go. So something is wrong here. Probably because append operation is applied to too few arguments. So I'm giving the target, the arguments, and the bytecode. What does that function want? It wants, of course, it wants the output registers as well. So here, it is very tempting to introduce a helper function that does the thing for me, which would be just gonna call it go. And go is append operation with the output registers. There we go. Ah, now this is a problem. I'm gonna comment this out for now. This is a stack from list. In fact, do I want rearrange stack to take a list as an argument? Because in almost every single case, I will give it a list. So maybe I should change, instead of doing this, I should change rearrange stack to be taking a list. Here's my desired state. And that means instead of stack contents here, well, first this means toList is no longer required here. And it just means I need to do the desired contents, which are gonna be a hash map from list with plus of map comma 1 on the desired stack. There we go. So there's a few places where this is going to make things easier. What are you complaining about? Oh, I forgot to open this as a do block. So this was interpreted as being argument 1, argument 2, argument 3, 4, and so on to something else. Okay. We are at imports that are not required, which is warnings that are in fact errors because I have made them so, which is good news, which means we are down to the last few remaining things. Defined but not used target. Yeah, I need to change this. Okay. Okay, that compiles. That's good. Let's go back here. So let's define a function R that does this and a block which was this nonsense. This is a block of the AR that, given a stack that starts with register 1 and 2, adds them into a register 3, multiply R3 with R1 into R4, compares R4 into R2, compare for less than, and then returns just R5. Now, if we do a generate block bytecode of this, that doesn't work because the type of it requires a label as well. So this requires a label, and the label is for now a function name and an address, I believe. No, a label is just 2 numbers for now. Label 00. Okay. That gives me a generate thing, so I can do a run generation. Oh, I'm gonna need to import stages generation in scope and monad. There we go. So I will need to run generation with a function name of generate block bytecode with a label 00, and the block we have just created is string name. Okay. How do we create a name again? There is no is string. Okay. could I use a built-in name, perhaps, for now? Let's say void name for now. Well, or maybe I just create... I could also probably just give it undefined. No, because my types are strict and therefore undefined would crash. Okay. So now this is run generation with the function name of generate block bytecode for this block, which as a reminder was this. So we start with entrance for the label 00, 0. Then we do a duplicate, push int 3, push int 2 roll, because we have R1 on top of the stack and it needs to survive this add operation while R2 doesn't. Okay. So it means we duplicate, so we have R1, R1, R2, we do a push 3, push 2 roll, which means we have R1, R2, R1. Okay. Why do we have a duplicate again? Because then we have add, multiply, greater, push into, push in one roll, return, which I think is correct. I am not sure this is, though. So I duplicate R1 into R1, R1, R2. I roll 3, 2. So I have R1, R2, R... Oh, I have R2, R1, R1, because I rolled 2, not 1. Yes, of course. Now, why do I duplicate R2? That's the thing that... Oh, because it is needed later. I've changed this function, of course. Yes, that makes sense. So now I push both of them. And then I just need to do a push 3, roll 1 to get the stack in the correct shape, roll, and then everything becomes, yeah, okay. No, that makes sense. That works. So we didn't break anything, which is always good. Which means, in fact, I might... establish a safe base of this is something that works before we go on to breaking everything by adding more stuff. Okay, so now with all of that done, I want to go back to doing the translation of instructions that have not been translated yet. I need to do branch. That's a big thing that isn't done yet. Is anything using register size at the moment? Nope. Not great, but that means I can just delete this function for now. Okay. So now this module contains generate bytecode, which is our entry point, generate block bytecode for a block, instruction for a given instruction, and terminator for a given terminator, it is clean, and then we have local helpers. Just this annotate and the terminator registers. That's clean. Okay, that's a lot cleaner than it used to be. No, now, so first, I think I want to go back and fix this assign. So we have here an assign where we have an int literal and a target. Here, there's not a real need to do a big append operation, output registers and stuff. Do I have anything? I have the append instruction, append roll, but I don't have a basic push. Let's do that, because that's useful. Append push given a do I want to generalize this to either a literal or an address? Probably. I think it's fine. Append push can just take, I think, a register name, an instruction buffer, and perform an action in the generate manner. I think that's fine. And what this does is modify the stack to do a stack push of the register while doing a append instructions of the instructions, basically. So this becomes a simple append push of the target, and the instruction is this. It's a bit ugly because push takes an arbitrary list of instructions, so this could be completely arbitrary, but I think it's fine. Okay, so now let's do exponent. And exponent is where things get really, really tricky. Because exponent is, in fact, it's gonna be. Let's write it down as a comment, and let's see where this leads us. So our stack is going to be at first arg1, arg2 probably, or we can probably start with arg2, arg1. And we are probably gonna want to have some kind of buffer here initialized at 0. Then what do we do? We are gonna basically want to do a branch if 0 to a end label, which is not something we can do, so we're gonna have to break that down. And have a address end at some point that then shifts the stack into the correct shape. So we don't have a way to do jump if 0 to end, so this is going to be a duplicate, arg2 being the exponent. Actually, it's going to be 1. Duplicate, not. This will be 1 if that thing was 0. Branch and if it was 0 or a loop otherwise, I'm gonna need a label here. So this is gonna be the address condition. Branch and loop on the current top value of the that's even more complicated because branch is not something that takes stuff as an argument, which means I need to push the address of the branch and then pop it if it's not, if I'm not going there. Okay. So to do a branch to end, if this is true, I need to push address end roll to 1. I'm gonna like label it this way because just for convenience, this is gonna be a push 2, push 1 roll. After which I will have not arg2 basically and address and then arg2 arg1 and the accumulator. I branch to end, which means if this is true, I am popping it and I'm going to this address. Otherwise, I need to pop to make sure I am back to having arg2, arg1. This is the body of my loop. I can do push int 1 subtract to remove one value of this thing. Then I need to bring the accumulator and the arg1 to the top of the stack. So I need to do a roll 3, 1. Now I have argument 1 and accumulator on top of the stack. I do a duplicate. After which I have arg1, arg1, accumulator, arg2 on my stack. Which means I need to do a roll 3, 1, a multiply, after which I have the new accumulator, arg1, arg2, and I need to rotate that a few times again. Maybe I want to do a roll 3, 2 here. That doesn't change anything. That doesn't change anything. Yeah, doesn't change anything. So here I need to go back to this shape here, which means first I need to roll 3, 1 to put the accumulator at the bottom of the thing, and then I need to swap those two, so that's gonna be a roll 2, 1. And here, after this, I can do a jump unconditionally to the address condition, which means I can just do a push address condition return. When I get to the address end here, that means I did branch from this place, and I end up with arg2, arg1, and the accumulator. I can do pop, and I will have the accumulator left on the stack. Okay, this is what we need to generate for an exponent there. Okay. So the interesting bit is I am going to need a few more addresses there. So I am tempted to go back here, append address, which will just give me the address. It's gonna do that by, so bump inner index becomes basically a helper inner function not seen by the rest of the code. That's fine. So I get the sub label index by doing a bump inner index. That means I can get a label which is, oh, I will need to know. I will need to know the current label of the block. Okay, so that means the label needs to be given here. Generate with needs to take the label here as well. And maybe instead of getting a sublabel index, I just do a label. So this is going to be for now just a label 0, 0. Generate with puts the label sublabel, which was actually not reset, which was wrong. So it needs to be there. And what I need basically, append address, is give me a new, so bump inner index is going to become bump label unless I just bundle it with, and I therefore remove this function, which I think I might do. This becomes give me the current label. Label xy is the result of doing a use of the generation context sublabel. I am gonna do a increase on the y value. This is a new label. Hello, yeah, this is my big Thursday stream. I am less tired than yesterday, so I'm less confused by basic mathematical operations, and there's so much I want to do this evening. And we're making a lot of progress. So the new label is the label x with the inner counter bumped by 1. obtained from the state, we need to persist that, so the GC sublabel is being overwritten with the new label. And we return an address, and an address for now is just a tuple of function name and new label, and the function name is obtained by doing a view of the GI function name. Okay, and all of this goes away. Oh, except no, before we do all of this, I also need to append an instruction, which is, oops, I append an instruction which happens to be a address entrance instruction with an address which happens to be this. In fact, I probably don't need that. Do I? No, I need the address to be returned because I will need to do a push address later on. Okay, so that's the address. I append an instruction entrance for that address, and I return the address. Okay. What else do we need given this nonsense? I will probably want to add... Maybe I will want to do this thing where I could change to have append jump, append branch, basically, as functions, therefore simplifying this. I'm tempted to do that. Let's do that. So this might just return the label because the other part of the address is the function name that is not required. Because it's all within the same function. So append jump will be given a label. I am jumping to that label. Put a jump instruction into our buffer. Target. This will be and a append instructions, and this is going to be, I think, straightforward, but I might need the function name. Yep, I will need the function name. It's that. So this becomes append jump to the target. Oh, this is not more complicated than this, because this one requires target arguments. It's just that this becomes append jump to the target label. And this is no longer required. And this is what I'm going to copy here. This is append instruction, which is first we append a push address instruction with the current function name and the target. And then we append a return basic instruction. Just going to be consistent. Okay, and this probably just doesn't need to give me anything. And append branch, and I think gonna be interesting. So this is gonna assume that the top of the stack is the value that can go away, can be popped. I need to be extremely careful. I think this messes up the shape of the stack because a jump by definition removes the address. So I think I need to be extremely careful. Any jump needs to be followed by a given address. Because it leaves the stack in a state that's wrong. The whole point of isolating those functions, append address, append push, and so on, is that they maintain the shape of the stack underneath. Append jump destroys the stack. So maybe I think here what I'm gonna do is I'm gonna modify the stack to be empty. The idea being, if we ever try to do any operation after a jump that is not an address, it is wrong and should crash, basically. Okay. And so an address needs something else. It needs the shape of the stack. It needs the shape of the stack to know, okay, when we arrive at this place, this is what the stack is like. Okay. Will this be a stack? Will this be a list of registers? We will see. Now, branch is going to be even more interesting because, again, we assume that the top of the stack is the condition. So that means we need to append an instruction which is the push address. So this is an append push. I don't necessarily have a register name for this. This is basically a big unsafe thing where I'm not using actual registers that existed as part of the code of the IR. I am inserting code that bypasses the existence of registers. That means I have to basically do the unsafe stuff and ignore stack management altogether for this. This is all unsafe stuff. That's fine. That's fine. Except for the roll, maybe, because the roll function does modify the stack underneath. I think everything else here has to be unless I create a notion of a dummy register, which should not be allowed to persist beyond this. What is a register again? It's just an index and a type. It's only using the index as the equality. Could I make a decision that a negative index means temporary register not part of the IR? That's ugly. it's not the end of the world. Especially since here I know for a fact that this is always going to be a register of type number, of int type, because that's the only thing on which we can do exponents like this. So maybe I can create fake registers. Do I have... I don't have... Interesting. I thought I had a pattern for like int register or something. I don't. Interesting. Let's do that actually. Because that's useful. So for a register, I will want to do something like this. I will need to enable pattern synonyms into this file. Okay, so here what I want is probably just for those. But now I'm just gonna do that. An int register is a register that's given an index. Yeah, it's quite useful. It's an extension of the language I don't use often, but sometimes can be very useful. Especially because it's a bidirectional pattern. I'll show what I mean by that in a second. So this will be a register of that index and of int type. There we go. And I can probably, as a result, make a... do I really need this? I mean, it's not bad to have, but maybe I don't need that. And I think I will just want to do a fake register function that's given to an int and given int, a fake int register will give me a register, and that fake, I guess fake register could be given a type. Let's see. For now, let's just do fake int register, and it's gonna be given some index. Do a register with minus the index and an int type. So the idea of patterns is I can use this to create. Here, I could use this to create a new register as being register R1 is an int register like 1 or something. And that creates it as if this were a constructor. But I can also do it the other way around. If I have some register, I can use it as a pattern. So int register R is my register or something, and it decomposes using the pattern because patterns are bidirectional. I use this quite a lot for built-in types, where the names have like a thing like this. That way I can use int name, and that's a name with this, but I can also decompose it if needed in some places, which means I can do pattern matching against int name, character name, and so on. It's pretty neat. So here I think if I try to keep this, so I will need the accumulator is gonna be a fake int register 1. I will still need to reset the stack with the address. Did I do that? I was in the middle of doing branch and I got sidetracked. Because branch will assume So this will be a dummy register. This will be a dummy register of type int that will be consumed by the branch, is the thing. So here I can use that. Let branch address. That's gonna be a fake int register. Oh, but I need to know the index. Ooh, I need to be very careful. Because if I use the same int register that I've used before, I think it's fine in this case because I'm gonna be popping it immediately. Oh, that's gross. That's gross. I guess I could assign some unique codes to all of them. This is fake int register 100. Because then this is an append push of the branch address at the top of the stack using a push address here of the function name and the target label, which goes into this register, branch address. Then this is the append instructions branch, the actual branch. Wait, no, because the branch needs to be on the condition on top. So first, this needs to be an append roll to 1, so that I bring the condition on which we do the branch to the top of the stack. The address is below. The branch instruction will pop the condition. This will pop the condition. In the case where we branch, it just goes to the address. In the case where it doesn't, then we need to pop the address which is no longer used. So that's a pop, which means I need to keep track of this if I want the stack to be consistent. So I need to make sure that I pop the stack as well. And at the end of this, I have popped the condition. And I have popped the address. Actually, I need to pop the thing twice, because this branch will pop the condition. This will pop the address. Okay. This is tricky. This should be fine now. So let's go back to this. So first, I will append a push instruction into my fake register accumulator with a value of 1. So this is going to be a push int 1. Then I'm going to rearrange stack to be in the order arg2, arg1 accumulator. Hence the need for it to have a unique index so that this works. Then append address. And this append address will have a modified stack. I'm gonna actually give it as a list in this case. This is gonna be a list of a register. And the stack will be a stack from list. Here it's unchanged, but I still want to make it clear that this address expects this shape. Next, we append guess that's an append push in a sense. Append duplicate could be good. The big problem is like I am doing a bunch of stuff that doesn't really matches with the logic of keeping a list of registers in between. So maybe this is the part where I do a trust me and I just say this is what the stack is at this point. Maybe all of that stuff about jump addresses and everything, keeping track of the stack is not really required. Because what matters is the stack, for the stack to be correct at the end of this function. And at the end of this function, it will be just a target instead of those two things. So maybe, rather than trying to fit all of this with a bunch of append things like this, instead, I don't pretend that there is any logic in this. I remove all stack manipulation from this. I remove all the fake registers from this. And instead, yeah, I think it's better that way. So that means instead of having a bunch of append address jump branch, instead of having a bunch of append like this, what I'm gonna have is instead a generate address, which gives me a label and a corresponding instruction buffer. Here's the instructions that you have required, but they're not put into the buffer. That's for me to do, basically. Do I even do that? Yeah, I think it's fine to do it this way. So this remains the same. Sublabel doesn't change. Function name, okay. And now instead of modifying anything of the state, I return the label and this new buffer of instructions, which is a list containing an entrance of that. Okay. Generate a jump will be something that, given a label, gives me an instruction buffer. And that will be pure of that. We no longer take care of the stack. Okay. Generate a branch is something that doesn't do any of this stuff anymore and just returns a list of instruction, which is push address function name and target, push int to push int one roll to put the address below the condition. Branch, after which the address will have been popped in the case where the condition has been popped as well. Okay. So now we can go back here. And this will basically become something like that, where I want to do the job of getting arg1 and arg2 on top of the stack, except I probably want arg2, arg1 in fact. And I will need here a complicated list of instruction. So that will be the thing. We're like, okay, put the stack in this shape and then execute all of those instructions. And those instructions will, at the end, pop those two things and put this target instead. So as long as those instructions have the correct stack shape, it's fine. So fake register no longer needs to exist. In fact, I'm going to go all the way. I'm going to just remove all of that for now. I think even int register is not really something that's useful at the moment. I will need, however, to generate the instructions. For that, I'm going to need to have a condition label condition entrance. That's going to be a generate entrance, generate address. No longer a need for a stack there. This is purely internal GC sublabel kind of stuff. Give me an address for the condition. Give me an address for the end. Okay. And I will need to know how to branch to the end. So branch end will be obtained. Well, no, those things require the looking into the scope for the function name. That's why they are monadic like this. Branch end will be a generate branch to the end label. And what do we have else? We have a jump condition, which is a generate jump to the condition label. Okay. So that's the stuff that we're going to need to create the list of instructions. And our instructions are going to be a complicated thing, because it's going to be first it's going to be a fold of first we have the condition entrance, then we have a duplicate, that's not true. That's not even true. That's already wrong, because first we will need to do a... So first we're going to have a list of instructions, which is going to be this, and that. Okay, this is tricky. This is extremely tricky, but we'll get there. So first, we're going to have a push int 1, which is going to be our accumulator, which is this one, which we need to put below arg2 and arg1 that are on the top of the stack, which means we need to roll it, and to roll, we push int depth to push int 1 roll. So now after this, we do have arg2, arg1 accumulator. We can append the instructions required for the entrance. Then we have duplicate, so that we duplicate arg2, not. That's already done. Then this is a branch to the end. Which we have generated right there. In fact, I'm gonna do that. Which is the instructions required to jump to the end address, which we have not put there yet, but will be there in the code. And this will push the address of the end properly and then pop it afterwards. This will also pop the duplicate arg2. So after branch end, we're back to having arg2, arg1, and the accumulator. And we know that arg2 is not 0. After which we can do... So we've done the branch end and the pop. We can do this push int1 subtract to remove 1 from the arg2, which is the exponent. Then this is this logic here that I'm just gonna copy and paste and hope that I got it right. The things we have to do because there's no exponent instruction in Piètre. This reminds me of when I write brainfuck, to be honest. So subtract the exponent, roll 3-1, duplicate, roll 3-1, multiply, roll. That's ugly, but that should be fine. After that, this is just a unconditional jump condition. After which we have the end entrance to which the branch has gone, where when we arrive, we do have arg2, arg1 all the same and the accumulator. And the only thing we need to do here is pop, pop. Those are the instructions for this operation. Okay. This is monstrous. But yeah, to summarize this, we need to generate a new address, which means internally we need to keep track of how many new entrances we have created, because each of them needs to have a unique identifier, which is used for linking purposes, because jumps and links and everything, the addresses are assigned unique ints at linking time. So this needs to generate a new address for us. This is the label that is unique. This is the code to jump to it. Well, to declare its entrance in the set of basic instructions in Piètre. This is the address for the end. This is the label that we need to. This is the unique code that will give us the code for the entrance. Instructions to how to branch to the end label. Instructions for how to jump to the condition label. And now we push a 1 and we roll it below. We roll it below arg1 on arg2, depth 3. Then we have the entrance to the condition of our loop, in which we do a duplicate not, which will be true when arg2 is 0, which is our end condition. We branch on non-zero, but after the not here, so when actually it is when the arg2 was 0. Otherwise, we do subtract of the arg2, which is our value, and we multiply arg1 by the accumulator while keeping a new copy of arg1. We jump unconditionally back to the condition entrance here. And then we have the end entrance where we just pop the stack. Okay. Whew. It's gonna be one of the first things whenever I'm able to actually generate images. That's gonna be one of the first things I have to actually test because this is a lot. Okay, so first, let's make sure this compiles because this is absolutely not gonna compile because I have made changes to this that append, jump, and so on no longer exist. So yeah, I suppose I could just append here. Append jump doesn't exist, but I could do an append instructions of a generate jump towards the target label. That way I'm still reusing those generate functions I've made. And here for branch, now that's interesting. Let's make sure this compiles first. Then let's do the branch. Ah, yes, this returns an instruction buffer. Huh. I guess this probably works still. That's kind of funny. If I do Z is this and sucks of this by doing this from a pair 1, 2, and Z is 1, 2. Aha, so Z matches before the view is applied. So if I do this, I need to keep track. Yeah, okay. So this doesn't do this doesn't do what I thought it did. So I have to be very careful. Which means new label is label xy plus 1. Okay. There's a bunch of places here where I have to be clear that I am talking about the bytecode instructions, not the IR ones. Oh, yeah, roll. Oh, damn it. Yeah, roll 3-1 is not a thing that exists. So this needs to be a push int 3 followed by a push int 1 into a roll, which is the same thing here and the same thing here followed by a 2-1. Oops. A roll. Oh, god damn it. Yep. Roll and roll. There we go. The odds of this being right on the first try are basically 0. So let's... I am tired. Let's try to follow this. This is arg2, arg1 and the accumulator at this point. So now I push a 1 and I subtract. So after pushing the 1, I have this. After subtracting, I have the new arg2 minus 1. Okay. After this roll 3, 1, I have arg1 accumulator arg2. Duplicate, I have arg1 accumulator arg2. 3, 1 roll, I have arg1 accumulator arg1 arg2. Multiply, I have the new accumulator and arg1 and arg2. Roll 3, 1, I have arg1 arg2, the new accumulator. Roll 2, and I'm back to having arg2 arg1 accumulator. Okay, that looks actually correct. One might hope that it might be somewhat... We'll see. We'll see when we can test it. Okay. Next, what else is wrong? Condition entrance. Is that not an instruction buffer? Perhaps I need to give it the fact that this is a list of instruction buffer, which means those things are instruction buffers. That sounds okay. Do I have overloaded lists, okay. Will that be happy? That is happy. Okay, perfect. And I can probably... That's fine. This is basically me forcing, okay, the traversable thing, since I have overloaded lists enabled, a list literal could be anything that is a list. So here I'm telling fold, actually this outer one is a list. And then within it, each argument is an instruction buffer. So this list literal is an instruction buffer. This thing is an instruction buffer, and so on. Okay. So that compiles somehow. So now I want to tackle branch here, which is complicated. Because a branch like this at the end of a block, the thing is, here the targets might have different stack shapes. As long as where I'm going, if it is true, as long as where I'm going, if it is true, is a strict superset of where I'm going if it is false, then it is a trivial case. Okay, so let me do the same thing that I've done earlier, and let's write some pseudocode in the comments. So here we will start with a stack that contains one register, which is our condition. I'm expecting a boolean on top of the stack. I'm not checking this, but if everything before has been correct, this should be a boolean. So now what we can do is, there is the first case in which there's the first case. Maybe I'm gonna do this in a both case situations. I'm not gonna try to like optimize right now. So this is going to be a branch instruction. So first we branch on this, the condition register gets popped. That's fine. And this branch, so this needs to be a push address of a temporary location, jump true, and we do a roll, then a roll to 1 so that it is below the condition. We branch, which consumes the condition. If we did not go, it means the condition was not true. We can pop the address that we have pushed there. And now we are in the case where the condition was not true. So we can rearrange stack. We can basically rearrange stack for the target thing and do an unconditional return to that label. We can do that basically. After which we will need the entrance for jump true. I will need the entrance for jump true, which is where we jump in the case this was correct, where we need to do a rearrange stack again, and then a generate jump to the true target. Because the stack might be different in either of those cases, and I don't have room in the shape of the branch base instruction to do stack manipulation. So this is what we need. So we're going to need only one address. So I can just, copy this. This is the jump true label. Well, true temp label, true temp entrance. Then we will need to know how we branch towards the false target. And we will need to know how we jump. No, in fact, branch will go to the true temp label. It's this one, jump true. We will need to know then jump true, jump false, which are true target, false target. And this will therefore be a... I kind of want to use the append operation there. At the end, this is going to be that. Those are the registers that need to survive. So that's basically, yeah, okay. Okay, so that's the registers that need to survive. And an operation is... I don't think that's true. No, I don't want to use the append operation. Okay, so I think I will change one thing. In this append operation thing, I have this rearrange stack thing. I think I'm going to do an additional function here, which is rearrange arguments, which is taking a list of register as well, but the hash set of register. And which does an action in the generate monad, and rearrange args is going to be output registers args is going to be this part here, which means this becomes rearrange args. Okay, so now I can use this one in isolation without needing the full thing here. So now this becomes, at the end, a rearrange args. I've already I already know here the set of things is the terminator registers. Okay. So here, if I have a terminator, I can do a case terminator of, which allows me here to do a rearrange arguments. My hash set of registers that need to survive is the terminator registers of the current terminator, which is, in fact, I don't need to do that. I could just do steal a case here and name it here when required. And I want the argument on top to only be the condition. That's the only thing I need. And if it isn't part of the jump arguments, it can be moved. Otherwise, it needs to be copied. That's what rearrange args does for me. And now I have the temporary address for the true label. I have everything. So now I can append instructions. And I don't need to modify the stack after this because this is the end of the block anyway. And the instructions will be fold of, first, we do a branch to the true temp label, which is the branch true. Then if we have not Damn it. Here I'm gonna want to use a thing where I do the rearrange stack, but the problem is I need to do it knowing the shape of the stack. So if I want to do that, I need to maintain the shape of the stack correctly. This is frustrating. So this is going to be append the instruction for the branch true. Then it's going to be rearrange stack again, but with the target arguments of the false target. But this makes assumption about the shape of the stack, and the shape of the stack is not the one that is there because I need to pop the condition. The condition has been popped by this. So that means append unsafe pop. No, that's not an append. Unsafe stack pop. I think I have no choice. At some point, I need to expose the No, that's better. There's a lot better. There's a lot better. I don't need to do that. Instead, those rearrange stack and so on, I think I'm gonna be clear. I'm gonna change the naming scheme here to make it very clear that those append modify. So this would be append rearrange args. That modifies the shape of the stack and everything of the instructions. But I could do a generate that, given the shape of a stack, that I know and control, okay, so I will need current stack gives me a generate a list of register. Current stack is gonna be a uses gc stack to list. I'm pretty sure I've done this before. Yep. So that means I need to be careful. This cannot be named current stack because that's gonna conflict, but this is stack current stack. There we go. Append rearrange stack. Okay. And now I think I'm going to rewrite this function again. as being, so this is stack get the current stack and do an append instructions of generate rearrange stack. So give me the instructions to rearrange the stack based on the current stack and the desired stack. And this becomes generate, which does not even need to be it does if I want to, god damn it. If I do this, then all of these nice append full stack roll and so on, god damn it, that becomes a mess. Because I need to keep track of the stack. I could do something horrible. I could bracket this. As long I don't mind doing things that are really horrible. As long as the API is clear. Can I bracket the state there? No, okay. So let's do that this way. This is going to be ugly. This is the starting stack. And now this is where it gets tricky. This is where haha, no, I know. I keep this. I'm gonna go back. Okay. This is append rearrange stack. It hasn't changed. However, we can do a generate rearrange stack. That is ugly. That is ugly. That's the worst thing I've written this evening. Previous stack. Current stack. GC stack is set to the starting stack. And this gives me an instruction buffer. So this is basically with a temporary context that has been so I have a with something, right? Yeah. So it's basically that. It's basically this. do I want to enshrine this as with temp context and with temp context will take the shape of the stack and an action in generate and will return an action in generate, and with temp context starting stack action will be stack is get the current stack, buffer is well, in fact, no, this is use gc stack, use gc instructions, set the stack to stack from list starting stack, set gc instructions, basically that again, get the result by performing the action, and then restore them to what they were. As if nothing had happened. That is ugly as hell. This is bad. But the upside is now I can do a generate rearrange stack based on this function that basically does with temp context and a starting stack do append rearrange stack towards the desired stack, and then extracts the instructions. And this will give me the instruction buffer for doing this as if I was in this stack here, regardless of what the one was before. That is not very elegant, but with that, I need two of them. I need to rearrange stack for, so true stack will be generate rearrange stack towards, this is not correct, those are labels. This is the target argument of true target. This is generate rearrange stack, where I need my stack to be the target argument of the false target. And in both cases, I need the shape of the stack to be, the shape of the stack will be so first I do this. I rearrange everything so that I have the condition on top. The stack will be the current stack on which I do a drop one, because the top of the stack will be this condition buffer that I need to ignore. But I need to take the version of the stack that contains this. So this is that. And in both cases, I will be doing a generate rearrange stack from this stack to this. Okay. So I have appended a rearrange args and gotten the stack, which means here all of those are now append rearrange stack, append rearrange stack, append rearrange stack, append rearrange args, get the stack that I can use it to do a bunch of generation, generate an address for the thing, generate a branch, jump, and the rearrange. And now I don't need to do all of that stuff. I can just do append instructions of fold. And I might not even need this, because the first thing we do is branch true, which is the instructions required to branch to this label based on the shape of the stack. Then if we have not branched true, then we need to do the false stack, which is the instructions we have generated here, to make the stack be in the correct shape for this particular thing, after which we jump to false. After that, we have the branch true was branching to a temporary label, so now we need the true temporary entrance, where we can rearrange. So that's the true stack, and then jump true. And those are the instructions for a branch. Okay, that was a lot. Let's see what's broken. And let's see what's not. And then let's test things. This needs to be... Yes, this gets a result. Oh, hello everyone. So here the result needs to be returned. Okay, so here the fold is again slightly confused. I'm gonna give it arguments so that it knows. I think this might be enough, in fact. Okay, this compiles. So now let's try it. Let's try to debug this. Well, debug. Debugging implies it's buggy. It might not even be. Okay, so let's try again. We recompile in GHCI. Let's define a quick R function to create registers for convenience. And now let's try, I'm gonna need a function name here, and I'm gonna need a block. So what instructions are we trying to compile this time? In the IR, let's try something simple. Let's imagine a function that gets one register as an argument and does a comparison with 0. So compare equality with some into a register R3. That's wrong. I'm gonna need, this is gonna be, I think it's fine. Technically, the comparison would put something into a Boolean register. As far as this is concerned, I think it's fine for it to pretend that the comparison goes into a register that's an int. Okay, so we are gonna then push an int into register 2, and that int is 0. Then we are gonna compare for equality register 1 and register 2, storing the result in a result result 3, in a register 3, after which we will be done with the instructions for this block, and we will jump. So we will try. We want to try to do a. Let's try first with just this for now. So push int is not in scope. Is it because I have done a misspelling, or is it because that's because I'm using the wrong import? This is a byte. In fact, I don't need to name it. It's fine. Okay. Push int is applied to 2 value arguments, but its type is not. Oh, of course, I'm wrong about this. I am using bytecode instructions. Well, here this should be the IR, of course. So no, here this is the IR. This is our input to our code generation. I may be tired, as you might have noticed. So this would be an IR comparison, and those are compare equal, where I store into R3 the result of a comparison between register 1 and register 2. Okay. And of course, push int doesn't exist. This is assign I. Okay, so now we have a block of basic instructions. We can try to generate block bytecode of the function name and the block. And what do we get here? Oh, this needs a label, not a function name. Have I not done? Yeah, there we go. Okay, so now for this, we get those instructions. Push int 0 duplicate. Interesting. Why would I duplicate 0? Why would the 0 get duplicated? I think this might be a mistake. Because our stack starts with R1, and then we push. Wait, I'm looking at the wrong thing. This is the block. We assign 0 into R2, which is this push int 0. Why do we have a duplicate? Oh, I think that's because the comparison for equality requires doing a bunch of complicated things. What if I try with a block that's easier for now to test things? Let's just test greater than. And this is just push in 0 greater, okay? Which is a lot easier. And then it is the roll for the return. Okay, yeah, that makes sense. Yeah, this complicated stuff is because of the duplication for the comparison for equality, because equality doesn't exist. Greater is the only operation I have at the bytecode level. Okay, so what I wanted to try here instead is I want to try a branch, because those are the monstrously complicated things we've just done, where here I'm going to be branching at the end on R3, which is our Boolean register there. And I'm just going to make up 2 labels that don't exist here. But the target... What is a target again? It's a label and a register, okay? So in the case where this R3 is true, I want to go to I want to go to a fake label that doesn't exist, label 1 1 with R1, and otherwise I want to go to a target of a label that doesn't exist, 2 2, and an empty stack. That way we can test that the reorganization of the stack works in both cases. Okay, and run the generation. There we go. So now what do we have? We start with the same push int 0, push int 2, push int 1 roll. Interesting. Duplicate. We have to duplicate it because we have to preserve it later on, I guess. Oh no, because we have to duplicate R1 is why. Then the roll happens, then the greater. Then we duplicate R3 because it's our condition there. We push it below the stack. We have 2 rolls in a row that do similar things. Those will need to be merged. We push the address of an inner label 1. Oh, I need to be careful with the thing. Branch pop pop push address. Okay. Return entrance, and where in this case it is just a pop push address return. Okay, that seems to be working. I am kind of tempted to try because I could already I'm kind of tempted to make a very basic test that starts generating an image from this. Let's try. I think it would be fun to try. That still needs... There's so much I have to fix to do that. But I kind of want to try that. Or maybe let's do it with GHCI for now. So linking will be... Okay, so if I run this generation, I get a list of instructions. If I import the linking thing, I can then do a link of a singleton, which is function name, and links to that list of instructions. What's the type of this? This gives me... It needs the name. Ah, the main. Okay. The main will be the function name as well. Error, okay. So I have a branch somewhere that goes to a place that's not found. I know what's happening. When I did the link here, I did not have in mind the notion of sub-label indices, which means the problem here is I find a jump, a push address before the entrance to that thing. Which means I have two options. One, I change the linking phase so that first I collect a unique address for everything, then I replace them, which I think is a lot better. Or two, temporarily, in here, I make sure that the entrances are always before the jumps to them. That cannot happen. Because if I have an entrance, I will need to jump over it. So no. Okay, I have to fix the linking. Okay. I have to fix the linking. Okay, so I could use a lazy state. I could use a lazy state. Yeah, I could do that. Okay, so let's sidetrack the code generation and let's fix the linking because I want to make an image of a function this evening. Let's do that. Oh, it's late. It's fine. How long could it take? First, let's move this, which is a very old naming convention. Things have changed a tiny bit since I've written the linker months ago. So this will be the linking monad, or just a link monad, I suppose, which will be. It is already a lazy state. Interesting. I was already planning on this. I was already planning on this, and for some reason I didn't make use of it. Wait, I'm already doing this. I am already doing the final state as an argument there. I'm already doing that. So that means that the problem is not in here. That's interesting. This error happened at line 774. Well, that's in line 36. Okay, so as expected, I am looking in my state for a hash map of addresses. Is it because this forces the evaluation of... Let's see. So this fails when I do that. So let's have a look at the instructions. Let's do a traverse print. So I can have them one line by line. So I have an entrance first called interactive foo 00. Then I have a push address, which is something that needs at some point to know of a 01. But do I have an entrance for 01 somewhere? Wait, why do I have... Oh! I'm an idiot! Of course, I've created here a fake block that contains fake instructions that point to label that don't exist, and then I'm surprised when my function doesn't actually work. Yeah, that's not very smart of me. Okay, so let's... Do I want to do this in GHCI? I kind of want to do this in GHCI. Nah, let's do it in actual proper GHC. In proper, let's do it properly. Let's write a very simple thing. In our main right now. I am tempted to here at the end of this add a very temporary thing of getting the functions. So I should have, if everything has worked, yeah, if everything has worked, if compilation has worked, here in this case, I will have the IR, which will be a bunch of functions. So that means I should be able to, this should be a hash map. So I can get the main function by doing IRs of main, basically. Except this is not correct. Let's see. I am looking for hashmap name function. This is going to be a name. So this is a base name, which is this module name identifier. The module name in this case, I probably have a module name somewhere. There we go. Module name is right there. Oh, in fact, no. Okay. I'm going to want to do something else. Here I have a bunch of functions. So I have a hash map from name to function. What I want to do is find main of the IRs. I'm going to make like a separate function. Find main will be something that, given a hash map from name to IR function, will give me a name. That's all I need, I think. Find main will be head. That's ugly. It's gonna be go of hash map to list and map first, where go on a thing here is an error main not found. That's very temporary code for now. And go of a name and the beginning of a bunch of names. And this is just a find, but this is just a list find that I'm re-implementing manually. It's fine. If the base name the identifier of the base name of n equals main, then n, else go recursively. So that's a find, basically. So now I have my main function. For all of those functions, I can do... No, I wanted to do that. I want to have a look at generation. I want to look at generation. What's the thing? Generate bytecode is name function. Perfect. So now this is going to be all functions is going to be this is going to be a traverse with key, I guess. No, a map with key. A simple map with key. Oh, I'm the wrong. There we go. Map with key. To get a hash map of all of them. So I will do a map with key of uncurry generate bytecode of all of the functions. Then I can link them. Link is something that takes why do I get a list of int and instruction resolved? That's ugly as hell. Probably gonna have to revise this at some point. This is clearly old code. So link result will be doing link on all the functions using main function as my entry point, with the exception that this needs to be a to list applied on all of this, because I have not, because that code is old. That gives me this list of int and instruction resolved. And the assembly is just gonna be that. Assemble the result, and I get an image. So I can assemble the result of the link immediately. That gives me a result. And now the only question is, how do I print this image to... Because I have in the past used, so I'm going to bring back graphics image. graphics image. It's probably an IO module in there. IO, there we go. Write image to a file path. So write image to program.png of the assembly of linking of this. We should be able to have enough to start making an image. Let's compile this. This needs to bring a few things in scope. This needs to bring... I'm in the wrong file. There we go. I will need to have access to... Wait, why don't I have access to this? Oh, because there... Yeah, okay, it's fine. I'll fix that later. Stages, I will need generation. And I will need assembly. And I will need linking. I write image. Okay. I need name in scope. But name is already in scope, so I have a typo somewhere. In name base, not base name. Okay, we're getting close. This is the wrong annotation. There we go. Huh, interesting. Oh, wait. Map with key is already uncurried. Perfect. It's not giving me as... okay. Okay, so write image now is lacking... Let's see if I've ever used write image anywhere. I haven't, okay. So this is a thing of there isn't an instance of the type class to print this version of write image to be compatible. That's annoying. Because RGBA Word 8, it doesn't know how to make... Or is it just that the output format is unclear from this? God, I don't remember how this worked at all. There is a display image altogether. Do I want to try this instead? Display image. Let's go. Okay. Moment of truth. Let's do a very basic file that contains one function main. function calls don't work. So main is gonna do nothing, but there is gonna be a function foo that takes x an int, y an int, and does while x greater than 0 x minus 1 y plus equal y times equal 2 or something, return y. And now let's try. How did I call it? Test. I am not very original. Okay, so this doesn't compile. Role not found. Row identifier float. Huh. That is weird. Oh, I suppose this needs to return an int as well. Wait, is there more than one file here? Yeah, okay, I am not looking at the right file. That explains. I want to write this one. Okay. So that did generate some code at the end, including here IR and everything. Why did it not then open the image is the thing I wonder. Because there was not any diagnosis, so that this happened. So this did nothing. Just to make sure that I'm not running the wrong version of the code or something. This should crash at the end. In theory, display image opens a viewer of the image. Okay, so it does crash here. Makes a call to an external viewer. They set as a default. Oh, this is a non-blocking function call. That's why. Is there a way to make it blocking? Okay, let's not do that. Let's do a proper write image. Yeah, sleep 10 should work. But I want the image to be persisted to file so that we can admire the beauty of it afterwards. So this is still what I want to do, program.png. I might need to specify what this is, basically. But maybe what I need is to use write image exact. And give it PNG there. Okay, that seems to compile. Okay, so we got an error there. Not implemented yet. So we did run into... So this actually did get run this time, but something went wrong. Okay. In the assembly. Interesting. I got a negative push. Fascinating. How did I get a negative push from this? Oh, is it because I'm doing the minus equal one that gets translated? Let's have a look. Here, let's print traverse print all functions. Okay. So that's foo. That's bar. That's main. There's no bar. Do I see in any of this a push int that's negative? Let's copy that into a scratch buffer. I don't see a negative push. That's weird. Ah, but maybe after doing the linking, I have something that's wrong in the link? Oh, in zero, you're right. It doesn't have to be negative. It could just be a zero. It could just be a zero. That's correct. Good catch. Thank you. It's not necessarily negative. It could be zero. How do I push a zero on the stack? Yeah, I don't have an easy way of pushing a zero on the stack. That being said, this shouldn't be too complicated, right? Well, an instruction is encoded by the translation, the translation from one block of pixels to a block of another pixels. So if I switch from red to dark red, that's a push. The argument to push is the size of the pixel block, which cannot be zero by definition. So I can only push strictly positive integers. However, I suppose that in this case, I could be doing a resolve push 1. Well, a resolve push. Where is resolve push called? Okay, so that's just what instructions do I need, and that's basically that's the instruction that's to go to push a 1, and then that's the instructions to push. Wait, subtract. What's the order of operation of subtract? Subtract is second top value minus the top value. So I go 1 minus n plus abs of n plus 1, and then I add subtract. Okay. And there it is. And there it is, absolutely unreadable at this lens. Try open it in GIMP. I am delighted to present to you the first program generated entirely from code. It doesn't do anything because since the instruction generation for calling another function doesn't work yet, this main function enters and immediately returns. It does nothing else. However, this here on the right, this is our foo function. So we enter here, that's a push 2, push 1 roll, probably. That's probably massaging the shape of the stack there. And then we have an unconditional jump, which is... Oh, thank you for the follow. And then we have an unconditional jump, which is probably jumping to the loop condition. So this must be the loop condition. We can have a look here. So foo is first a block which is just a jump to label block 1, okay? That's the first thing we do inside it, okay. Oh, but interestingly, that is indeed a roll, okay, here. Because the block 0, the only thing it does is reordering the order of the arguments. The arguments are I0, I1, and they are reordered to I1, I0 for this block. So this is the roll that happens. Then we push the address, we jump. So this is where probably some optimization would remove the jump if we can fall through. Oh, I'm an idiot. Sorry, yes. Let me do this and... God damn it. I have changed my OBS layout recently, and I'm not used to having to... There we go. Okay. So that should be still visible on the layout. Okay. So yeah, this here is a roll because we start with I0, I1, which are the two arguments on the stack, and we switch them to I1, I0. Then we enter block 1. So this is where an optimization could be done to do... We don't need a jump here if we do a fall through, basically. But we enter this thing here, which is block 1. in which we do assign 0, which is the push 1, subtract. So that's our new thing. We do a comparison with 0 into B4, and then we have a branch. That seems wrong. That's a lot of stuff. I guess the branch is here. But that's so many operations before that. Oh, unless this is not block 1. Unless this is another block. No, because we start with the assign 0 here. So why is all of that stuff? Let's see. After the entrance into... Where is the entrance for block 1? I'm gonna copy this into a scratch thing. I am looking for label block 1, label inner 1. That's the label inner 0, in fact. There we go, that's the one. So here we have push 0, 3, 1, roll, push 3, 1, roll, duplicate. Oh, this is all of the operations so that this comparison operation followed by a branch has the things in the right order, because we have I9 and I2. Wait, that's still weird. Because we assign I3 0, which is push int 0. I guess no, it makes sense. We need to keep a copy of both I2 and I9 for the branch thing here. So it means both of them need to be copied. So that's why I have a roll duplicate. I have another duplicate here. Why is the second duplicate after the greater? That bothers me a tiny bit. Yeah, something is definitely wrong here. I do a push int 4-2 roll, push int 4-2 roll. That's something is definitely wrong here. Okay, so we'll have to debug this. So I'm not gonna yet be happy about this. We're not at a state where this works well enough. But it is starting to get there. It is starting to get there. This is still technically a program that was generated from a source code. Okay, well, yeah, at least it's an image, exactly. I'll take that. Now, what is missing for us to be able to actually test this? It's 1 a.m. I've been at this for almost 5 hours. I should probably stop here. I am tempted. Oh, yeah, no, okay. I was gonna say, I'm very tempted to try to do a tiny bit more just so that we can actually run those programs through an interpreter and start seeing what they do to debug them. The only problem with this is I don't have yet a notion of built-in function. So I have no way yet of doing a print of any value. So even if I did manage to, that being said, wait. I could run a interpreter with something that shows the shape of the stack with like the trace or something, and create a trace picture. I could still, despite the lack of print, if I fix function invocation, I can try to run through this and see what it does. Okay. I'm gonna cap this to maximum half an hour from now because I need to sleep. But let's try. Let's try to do. It's gonna be tricky. It's gonna be fun. Let's try to do one more function generation. And let's do. Where are the instructions? Let's do invoke n, which is invoking a function by name rather than invoking a function from a register. So no function pointers or anything yet, purely invoking a function whose name is known at compile time. So we can link against. So here we have two cases, which is where the result goes. We have the name, func name, I suppose. And we have the arguments. This will be somewhat similar to what we have done so far, in the sense that this will be a go with, but result might not exist is the thing. For the sake of just having something for this evening, let's just pretend that there is always a return register there. And this therefore becomes go with that target. This is where the return value of the function goes. So the stack will contain that at the end, with those args like this, regardless of what they are, and a bunch of instructions. And those instructions will be, and I'm gonna need to do some generate stuff again there, generating entrances and stuff. So I'm gonna copy this, because I need to create an address, which is the function return. So invoke return label invoke return entrance. I need to generate a jump to I don't have a label. That's fine. Okay, so this will be, what will the instructions be? Or is it just going to be a list at this point? No, I need, yeah, okay. So this is going to be, first, I am going to push an address, which is the function name and the label 0, 0, which is always a starting label of a function. So I push that address on top of my stack, and then I return immediately. Nope, that's not true. This will be how I call the function, but first I need to put below my stack, I need to push an address this function name. This function name will be obtained by doing a view of the generation info function name. So first I push something which is in this function name, the label of where we're gonna come back, which is the invoke return label. Hello, thank you for the follow. Then after this, we have pushed the address of where we need to return. We need to put this below the arguments to the other function. So we need to do a roll, the length of which is, the depth of which rather, is the length of the args plus 1. Again, assuming that all of my registers are of size 1, which I am assuming for now. And the number of steps is 1, after which we do a roll. So now we have the function arguments on top of the return address, which is this invoke return label. Then we push the address, which is the starting label of that function. We return from the current function. After which we need to put the entrance, the invoke return entrance, because we have jumped unconditionally. This is where we come back. And when we come back here, the stack is correct. We don't have to do anything else. This should be all of it. So I could, yeah, okay. Let's try to compile that. Okay, those are all bytecode instructions because we are doing code generation. So I'm just going to prefix all of them with BC. When I do the push of the address, this is the other function name because I am calling, and I think I have a start label alias for label 00. I don't. I thought I did. I was convinced I had a start label. Interesting. I do. Oh, but somewhere else. Okay. For the sake of this evening and finishing before it is 3 a.m., label 00 is good enough. Okay. So now we have function calls, which means let's try to do something a bit fun. Main will be calling Fibo 5, Fibo x, which is an int, will be if x is greater than 2, greater than 1, let's say, return Fibo x minus 1 plus Fibo x minus 2, else return return 1. So 0, 1, and yeah, okay, that should be fine. Okay. What's this? What is wrong with my syntax here? Semicolon here, probably. Yep. So that did compile. Let's have a quick look at how this is done. So here we start with I0, which is our integer. We assign 1, we do a compare, we do a branch based on this. That's our if. If it's true, we jump to 2. If it's false, we jump to 1. No, we jump to 3. My bad. And 3 is here. This is just assign 1 to the register and return that register. And otherwise, block 2, there you are, takes an argument an x, we assign something, we do a subtract, we do an invoke, we do an add, and then we return. Okay, that looks good. And when we do an invoke, we are invoking the name of test fiber, which is the same function. Okay. Let's have a look at the resulting image. So now this main does a bunch of push address and stuff, and then just that's the invoke that we have just created that calls to probably this address here and then puts this return address here at the end, where here at the end we should have a terminate that we don't. This is gonna loop forever. Okay, not great. Not great. Yeah, this is just gonna loop forever. Oh well. Because I don't have a way to actually terminate the execution yet. And this is our Fibonacci self-recursive function. Yeah, that's exactly what I'm gonna do, I think. It's still never gonna terminate, I think, which is a problem. Although I guess I could... Ba-ba-bum. Let's cheat just a tiny bit. I want the pencil tool, and I want black is perfectly fine. And I want that of size 1. Here we go. And we need to make sure that it is trapped at the end. I think I was using this design for my terminate block. Up. And let's pick a red, because why not? And do that. Because now it should, oops, enter this red block and be block on all sides. This should terminate the execution at the end. What? Is it because I did a save as instead of an export as, of course. Okay, there we go. So now this would be patched. Let's try now. What are the options for this? Let's do a trace. I kind of want to also do a create trace picture, which is this one. of program fixed. Okay. Okay. Does it give me at any point the shape of the stack? Action pointer, duplicate pointer, so on, so on. It gave me all of the actions. Okay. Oh ho. Okay. Okay, so that's pretty correct. Let me open this in GIMP just so that we can see it. Because GIMP, I'm using GIMP only for one reason, which is it zooms without doing interpolation. Okay, so that seems to be working. We enter this push 5, push 2, push 2, push 1, roll, push, and then this goes back out perfect. Oh. Oh. Yeah, I'm an idiot. This needs to be able to go elsewhere, because otherwise this is blocked. Okay. So let's patch our patch again. Because this needs this path. Ooh. This path needs to be free. But it should be fine to do this. Give me 1 second. Export as fixed. There we go. So this editor is Emacs. This is just a basic Emacs I've been using for, like, at this point, 20 plus years. And basically barely any configuration. It's very bare bone Emacs. Okay. Action pop stack is empty. That's not a good sign. Oh, did I not save properly? It looks like I did not save properly. Okay. Replace. Export. Okay. That looks better, I think. I'm looking at the instructions and I'm not seeing some weird... No, I did see a pop with stack is empty there. I don't like that at all. So let's have a look at the trace. Okay, so now we do go here. We push the instruction. We go back here. Perfect. That seems to be working. Then when we enter here... Oh, we never branch here. This is never true. That's a problem. That means x greater than 1 is never considered true. Okay, we have some bugs somewhere. Because that's a branch, I believe. And if it's not doing anything, then something is wrong. Yeah, okay, so we have a few broken things still. Now, could I... Yeah, exactly. We use GIMP to edit our programs. That's correct. Can I see with NP the shape of the stack? I guess there's a verbose option. Let's try that. Aha, so now I have the stack thing. Oh, will that decorate the trace thing with the... No, that probably would not. That would make no sense. Okay, but I can check... Um, operations 2526, where when we entered this function. So I can look at, after that, what we do. We push the value 5, we push the value 2, we push the value 2, we push the value 1, we roll. So that's a 2-1 roll. So that's 5 is the argument, 2 is the return address. We roll so that the return address is below the 5. And then why do we push a value 3? So we have 3, 5, 2. Oh, 2 is the return address. 5 is the argument. 3 is the address. And then we exit because we go to here, because that's entrance 1, entrance 2, entrance 3. So indeed, we have 2 as our return address, 3 as our address. We go there. Let's see, what step do we enter this? 70-ish. So here we enter with... We do a push 1 and we have 1, 5, 2. So 5 is our argument, that's our x. Then we have 2, 1, then we push again, and then we roll, and we end up with 5, 1, 2. Okay. Action duplicate, 5, I 1, 2. Roll, and so on. And then we have greater. So is 5 greater than 1? The answer is 1. We have a 1 at the top of our stack. So if... that's annoying. I can't compare with the... I would need to close this GHCI, stack, run this, and I want to have a look at so we've done the compare here, and now we branch based on the value B2, and we want to go to label 2, which is probably going to be the next address 3. Trace 152 here. That's the result of the comparison. Okay. We duplicate that one. That's interesting. I'm not sure why we're duplicating. That feels like a bug in my branch. Because here we have just done a compare into B2. And B2 is lost after this. It's only used for this. I don't see why I would need to keep it with a duplicate. So I think there's a bug in the generation of a branch. So here we start with rearrange terminator registers. Oh, that's the bug right there. That's the bug right there. Here, terminator registers considers that the condition must be in it. That's wrong. So here I am gonna just do, rather than naming this, this is gonna be output registers is going to be give me one sec. It's gonna be the from list of the arguments of the true target union the set of the arguments of the false target. Okay, and I just need to make sure I have hash set in scope. Perfect. It is the biggest compiler I've worked on. I've had a lot of other toy compilers before, and I've had a actual job in which we were working on a big project that was close to a compiler. It was generating an API for a GraphQL server based on the shape of underlying databases and parsing incoming requests. But the thing is, it was doing a tokenization into a parsing, into an IR, into a code generation. So it was basically a compiler in many ways. But this is the biggest compiler I've worked on, if you exclude one or two extremely small contributions to DHC. And here, Terminator doesn't exist. This is now output registers. And it is still kind of a silly project. I'm trying as hard as possible to keep the structure of this as close to a real compiler as possible, but we're targeting images. So, there's a tiny bit of this is for fun as well. And yeah, Haskell is my main language at this point. It's been the one I've been using for over a decade. And it's just the one I'm the most comfortable with. So here I will need to redo, since I have regenerated the program, I'm going to reopen the program. It's going to be a bit different now because I have fixed the duplicate that was wrong in the stack. And I'm just going to need to redo the termination here thing. It's just going to be that and that and that and oops, that. There we go. Fixed. Okay. I see a bunch of stack values 1. I think that's still wrong. So let's go back. Let's have a look. I should find an editor that, like a viewer that just doesn't try to do approximations. I want the trace. Okay. We enter this function here. We're still never branching, so something is still wrong with our branch. Around 70, okay? So now, 70, we enter. We have 152. That's correct. After a push of 1, 5 is our argument. So this is Piètre. This is an esoteric programming language in which the source code is an image. And so this is a technically valid but also buggy Piètre program that the interpreter interprets as being instructions by looking at the transitions between different groups of color. If we look at the trace there, this difference between this color is interpreted as a push instruction. The difference between this color and this color is interpreted as a roll instruction, and so on. And this compiler project takes Rust-like code, like so, and generates an image like this down the pipeline. So that's a toy. Even though the structure of it is as close to a real compiler as possible, our output is, no, this is not used in real life. This is a esoteric language used for fun, and that I'm targeting for fun. Partly because it makes it look like at the glance it's going to be a simpler example, like simpler use set than actually targeting a real backend. But in fact, it's a lot more complicated because I have to deal with the extremely limited instruction set of that language. However, one thing I'm planning to do as well is, since we do have an IR the same way as LLVM has, I'm planning to also do an export to the LLVM IR to actually really compile into an actual program, so that we can do diff of behavior between an actually compiled program and the interpreter running on the image. Okay, so here, what do we do? Push to push one roll. Okay, where do we do the greater? Here, greater. So we've checked that 5 is greater than 1. Okay. Then push to push one roll. So we're putting this 4, which is the address to which we go if this was true. Wait, do I have... So wait. When we do a branch, we start by putting a branch to true, but here I have a not before. Why do I have a not before the switch? Is it because of the way the assembly works? If I look at my templates and I look at branch, and yeah, it looks like I do a not there. Interesting. Why do I do a not there? Why do I want to branch on 0 rather than branching on non-zero? Oh, that's because I want to guarantee that the value is 0 or 1 and not anything else. Does that mean that I need to change? So if the register is true right there, oh wait, unless it is just a matter of file. No, I don't have a not here, so that is what's happening. So that means that if I want to keep this needs to change, and this becomes the false basically, because branch goes on the negation of what is on the top of the stack. So we branch false, then we have the true stack and jump true. Then we have the false temp entrance, the false stack, and jump false. There we go. Is there any other place where I generate a branch? Here, for the exponent, and here I can remove the not, because it was a not before the branch, but the branch does a not. In fact, this is branching to the end. So this is branching on the value being 0. Okay. And that's about it. Perfect. Let's this compile. It seems to be compiling. Let's rerun the thing. Go back here. I'm gonna close a few things. Reopen the program. That has been modified. Go back to just doing this basically and this and this, just because I don't have a proper way to end the execution otherwise. This goes back to being program fixed. And now, wait, wasn't it saved? Oh, but it's exported, not saved, hence the, okay. And now we can rerun this. Oh, I see negative values in the stack. I don't like this at all. I think we have something wrong. We have some infinite regression somewhere. Because our stack is growing with negative values and there shouldn't be negative values. Okay. Let's just go back to... That's about enough. 152 to 152, something, something, something. That looks good. We do the greater to compare with 1. We push the address, which is 4. We roll it below the condition, not the condition. Switch happens. This is 86. Here, 86. And since the value on top is a 0, we did not change, okay? So we did not go to the other branch. Okay. Wait, what's weird is even when it was 1, we did not do a hmm. Okay, this goes to address 5. And this is where I stopped it. So something might be wrong with this. Because this should have... No, it's normal that it didn't go into it. Hmm. Okay, let's try something. If I do a x less than two, if I change this to be in this order, well, I can just instead keep this the same. What if I do fiber of 1? I regenerate the image. I run on the program unmodified this time. I wait about 100 instructions. There we go. This is running on the unmodified that doesn't have the exit. And we still did not So here, this pattern doesn't work. So the logic of this was supposed to be that this is a CC operation with 1. Wait, why would 0 be here and 1 there? Pops the top value of the stack and toggles the CC that many times. So here around 70. Not switch. I am switching with 1. Oh, of course this doesn't work. This doesn't work because this runs immediately into a black wall here, and therefore understands it as like, oh, therefore we need to switch the CC again. Okay, we can fix this. I think if we introduce this, then here it will be forced to exit from this pixel, bump there, and therefore do that. Okay. Let me just think about this for a second. Yeah, it should be fine. Let's try again. I just hope that it does realize that it needs to recompile. It does, perfect. Regenerate the image. And I stop it here. Look at the trace. There we go. This worked. Now we have the switch 1, which goes here and exits the function properly. Perfect. Except it then just re-enters more stuff. Okay. So with that being okay, let's open the program again. Do our little fix for this as usual. I just need pop. There we go. And then I'm tempted to actually add it programmatively. Yeah, rather than doing this, let's maybe quickly go back to main. And I probably would like to change, as it's going to be too annoying to do. That's fine. So now I rerun on program fixed, and this should terminate now. It did not. That's annoying. So what happened with the trace then? Because it did go here. Oh. Did I just stop it before it... I might have stopped it just before it finished. Yep, okay, perfect. So that has worked. And let me just check at after the return at 239, we should have a stack that only contains... Why is a pop there? Weird. When we leave this function here, 133, we should be pushing back the address of main. Push value 8, which I think is our address, with 2 being our result, I guess? Nah, that's wrong. So why do we have a pop here? At 131. Because we enter there, and our stack just contains 2, which is weird. Because when we left 87, 88, oh, the 2 is the return value. But maybe we don't... maybe it means I have a problem with preserving the the return value of the stack. Because I do 4124 is the address. And I do a pop the second I enter here. Was that pop in the generated code, or is it a mistake of the code of the entrance? Let's go here. I don't see a pop after an entrance. So that's probably yet again a mistake that comes from assembly template entrance. No. Okay. So that governs the entrance. That looks fine. It's this. But then I have here a pop into a push. Despite the fact that if I look at the scratch, where is the push 8 happening? It doesn't happen. Weird. This was operation 132. I do have a push 8 here. I have a pop followed by a push 8 after entering this thing, which should be this address here, probably? Which is supposed to just be a push 1, push 2, push 1 roll return. How did I end up generating a push 8? Oh, it's the address. No, of course, it's an address. So it's the push address. Aha. Here I do have a pop push address after a branch, but not after an entrance. Aha, here it is. Here it is. I do an entrance pop push address. Is that because is that a bug in the generation of branches? Because I know this is where I have an entrance for the pop for sure. Yep, there it is. So it's probably, well, this one is the exponential, so I don't care. So maybe it's in the branch faults? Or could it be in the false stack? In fact, that's correct. Because yes, here we need to drop the stack because we don't need the one that's in it anymore. And then we push the address 8 to jump to it because we are jumping to the block. Because this is our branch and we are jumping to a block with no argument. We are jumping to block 3, which is this one, which is just return 1. That's why. So that is, in fact, I'm trying to debug something that is actually correct, okay? So when do I enter this thing here? 200 more or less. 200. My stack is empty except for 2, which is my return address. I push 1. I put it below the return address, which is 2. And then I return. And when I arrive in main back at operation 240 or something, not sure why there's a pop there. Probably because the stack is empty. Yeah, the stack is empty. Could I see? Yeah, and before that, the stack contained 1, which is the result of Fibonacci 1. So that is correct. Okay. So what if I now try 5 again? Let's maybe be less ambitious. Let's try 3. Generate the program. Reopen the program to add an actual termination condition again because we still don't have a way to do that programmatically because one thing at a time. That's the fixed program. There we go. Replace. Export. Let's run this. And let's wait and hope. This time I don't see weird negative values on the stack. I spoke too soon. I see negative values on the stack. Okay. So now we're going to have to debug the rest of the function. So now sometimes we continue there. Okay, so let's go back to around is it? I'm gonna run it again and stop it earlier than that. I think it's around 70 that we do the branch. There we go. Around... So this time we did not do the branch, that makes sense, and we did enter around 80, okay. So here the branch did not happen. That makes sense. So we pop the address, we still have 3, which is our argument, and 2. We push a new address, 5. We do a bunch of stuff. We arrive at step 97. Where is that? Where do we arrive at step 97? Oh, that's probably... I probably stopped it too early. Yeah, okay. Let's give it 200 steps and such. Yeah, more or less. Okay. Okay, so now they overlap. So after around 100, around step 100, where would that be? Ah, 131, there we go. That's probably the one. Because that's a push 1, push 2, push 1. Is that indeed in the block? God, this is unreadable. Is this indeed push 1, push 2, push 1? That looks indeed like the block. That's 0, 0. Is there any other block that does that? This one, which is labeled block 2, which is where we jump if it's true. Okay, so that's what it is. So this is 138, 139. So here, push 1, push 2, push 1, roll, duplicate, and so on, and all of that. What are we trying to do here? We are trying to subtract 1 from I4. Sorry, subtract 1 from I3 and put that in I5, and call the same function with I5. Subtract 2 from I7, call the function there, and add the return value I6 and an I9 into I10. That looks okay. So maybe something is wrong with the invocation? Yeah, my subtract ends up with a -2. That should never happen. So something is wrong in the code generated for doing the subtraction. So let's debug this. Let's see where 3 is. Entrance here for label 3. That's the one. Nope, that's the wrong one. Because I am looking at label... What block am I looking at? Block label 2. Entrance 2, 1. 2, 0 here. There we go. This is where I push the address and everything. Okay, so here what I do is I have my stack contains, when I enter this, value. So 2 is my return address from the Fibonacci function. 3 is my current argument. My push 1, push 2, push 1 roll, which puts... So I push 1 and on top of 3, which is x, and 2, which is my return address. And then I do a roll to 1, so I have x1, where x happens to be 3 at the moment. I duplicate, so I have x, x1r, 3 to roll, that's a roll 3 by 2, so that means 1xx r. Swap again, push to 1 roll, that's x1 xr. Subtract. I do 1 minus x instead of x minus 1, okay? That's because indeed this is incorrect. Because the order of operations is that the second top value minus the top value. So if I'm trying to do minus arg1 minus arg2, then arg2 should be on top of the stack and arg1 should be below. Likewise here, for this it doesn't really matter, but for divide it does, for modulo it does. For all of those it should be fine. Okay, so that's the error. Oh god, it's late. Generate a new image. Add just a tiny bit of help here so that the program may have a chance. This requires being red. And this needs be black. There we go. Now, if everything works, there's a chance this might terminate properly. I no longer... no, I saw some negative values in the stack, I think. Maybe not. Let's give it a chance. Let's run it and see what happens. That stack doesn't look like it's going back down. Ah, maybe? Nope. It did stop, okay. And at the end, the value was 3, which, if I'm not mistaken, is correct. So if we do Fibo 5, we should be getting 8 at the end. This is, however, extremely, extremely slow. I wonder if it's because I'm generating the image. Maybe I don't need to generate the image anymore. So let's just do that and that and that and that and that and that. Export into fixed, replace, export. There we go. And here I'm gonna run with trace, but without generating an image. That's a lot faster. And before we popped the stack, we had 8. We have a recursive Fibonacci function written in pseudo Rust that does end up compiling to Piètre. So to sum up what we have and why I'm happy with this, we start with this main calls Fibo of 5, which is here a recursive function that does, if x is greater than 1, call this with the thing properly, else return. We don't have a print here, but when we inspect the memory at the end, we do see that the correct value is there at the end. This is being lexed, pass, type checked, validated, and after the work we have done today, this generates a bunch of bytecode. So if we look at the output, actually, does it still write? Does this still write? Give me 1 sec to check something. Do I still write a HTML page with the thing? No, it looks like I don't. Oh no, pretty much HTML. There we go. I do have this. Okay. So that should be, I can probably open. This would be, it's called test. Obviously, it's called test. Okay, so that's the past version of our AST with just highlighting for the syntax. The validated version confirms that when we do call this Fibo here, points to this Fibo here, so it's the same, that is correct. This X is the same as this X and everything, okay, so that's the validated version of our AST. Then we transform that into an IR, which is modeled after the LLVM IR. So we should be able to convert this representation into the LLVM IR, where this Fibo function here does the, like has a bunch of blocks and jumps between them. Then we generate a bunch of Piètre bytecode. Then we link it because we are at this stage, we are referring to the bunch of addresses as like, go to that address wherever it ends up being. And then we generate This doesn't generate the LLVM IR yet, but this IR right there, um, the internal model is based on the LLV. Well, not based. I have thought about making it compatible with the LLVMIR, so it should not be too complicated. Famous last words to export from this to the actual LLVMIR, which I am planning to do at some point as an alternative backend to this compiler. For now, this is the IR we have. Yeah, the idea of using the LLVM backend would be we would be able to compile this program um, here to an actual binary and test it and compare that it works the same way as the interpreter. So it would allow for very interesting tests if we had this. Plus, it would also, validate all of the front end of the compiler by running into the LLVM backend for the backend part. So that's something I'm definitely planning to do at some point, but that's not done yet. So after all of that parsing, that validation, that gives us all of that stuff, that confirms where all the things are, does all the type check, we generate this IR, which is, again, somewhat similar to the way the LLVM IR works, a static single assignment IR. Then from this, we do code generation into bytecode, which is basically giving a name to each Piètre instruction. We do the linking, we do the assembly, and we get this beautiful nonsense. Now, I think the next steps are going to be next week. First, there are still a bunch of instructions here that we don't support. I don't support yet invoking a function with a register. So a function pointer, I don't do that yet. I need to implement termination, absolutely, which I'm probably going to do as having main being a special function that's hard-coded that just calls the main that we found in the program. So yes, I want to do the invoke R would be having calling a function that has in a register. I'm missing a bunch of the assign instructions, which I have no code generation yet. I don't handle references yet at the moment because the language supports references, but I don't handle them at all. They're gonna need to be threaded throughout the entirety of the IR to be part of the return of a function. So that's going to be something that needs to happen as well. And the big other thing I need to figure out is how to do built-in functions, because I want to be able to do readInt, printInt, because when we have readInt, printInt, I can remake this Fibonacci program so that it takes the argument from the command line and actually prints the result, rather than having to look at the state of the interpreter to know the shape. We are that close to the first program being properly generated. Okay, I'm gonna stop here because I've been at this for 6 hours and it's 2 a.m. and I need to sleep. I am just going to commit a few things. What did we change? So fix branch template. Here in the assembly, we've implemented assembly. We've implemented negative numbers. Then we've fixed so many things. Oh, I can remove that actually. That's convenient. What did we fix in the generation? I'm gonna commit this one on its own. That is fix stack generation fixed stack order of arithmetic operations arguments. Then what else did we do? I might just bundle everything else as implement. Yeah, because that's all the generate stuff. That's all the with temp context. That's all of that nonsense. So I'm gonna commit both of those as generation implement branching. Finally, generate program image. Okay. Well, that's gonna be all for this evening. It's exciting. We're getting close to having our first programs. We are so far from being a 1.0 because there are so many parts of the language like structs and strings and all of that that are nowhere near even started. But still, we're getting close. It's nice. Okay, well, thank you everyone for tuning in. That was fun. I will go get some sleep and I'll see you all next week.